Good morning. Welcome to the first International Symposium of Hanyang Institute of Energy and the Environment. My name is Park Jae-woo in Department of Civil and Environmental Engineering at Hanyang University. Before we start our main program, we will have Professor Kim Jong-yang, who is the chairman of Board of Trustees at Hanyang University Foundation. Let us welcome Chairman Kim with a big applause.
Good morning, honorable speakers, guests from abroad, distinguished researchers, and ladies and gentlemen. On behalf of the Hanyang University, I am very pleased to have this opportunity to welcome all of you to this first international symposium organized by the Hanyang Institute of Energy and Environment. Founded in 1939, primarily as an engineering institution, Hanyang University has dramatically evolved over the years and now has its sights set on becoming globally recognized research university. In line with this goal, the HY-IEE was established last year to provide a platform consisting of a network of professors and researchers in different academic areas to converge and promote innovative research on energy and environment. We believe that such a network will allow for the creation of an innovative academic cooperation model that addresses the increasing challenges in the energy and environment field, while also developing innovative solutions to related assignments and our mission. Energy and environment are two important issues of our era. By assuming proactive stance toward the various issues we are currently facing, we better prepare ourselves for the challenges ahead to enhance or even sustain our life quality for all ourselves and the future generation. We must act actively and responsibility, and the time is now. I'm confident that today's symposium will play a key role in promoting future international cooperation and will serve as a stepping stone on the path toward significant contributions to the area of energy and environment, both locally and internationally. Once again, on behalf of Hanyang University, I thank you all for your participation. I'd like to extend a special thanks to Dr. Stoner, Professor Logan, Professor Sovacool for joining us today. Please enjoy your educative and productive time. Thank you.
Thank you very much, Chairman Kim. President Kim Woo-sung at Hanyang University is here as well. We want to ask him to give a welcome message to all of us. Let's welcome President Kim.
Yes. Good morning, everybody. First of all, I would like to express my gratitude to everyone here for your attendance, especially for our international guests who traveled all the way to Hanyang to participate in this first international symposium of HY-IEE Research Initiative for Energy and Environment. Our world recently hit a milestone. Officially, the Earth now has 8 billion inhabitants. Needless to say, with this explosive growth has come a myriad of challenges, some seemingly insurmountable. However, with human ingenuity and resolve, we can surely overcome the obstacle we face ahead of us, although admittedly not without some trials and tribulations. Thus, international events such as this one today are crucial if we are to effectively address the wide range of energy and environment-related issues we are facing. I'm confident that HY-IEE will play a pivotal role as a global platform where the scientific community, related industry and technology can and will work together to enhance the knowledge and skills that are needed to resolve contemporary and future energy and environmental-related problems. In closing, I'd like to express once again, thank you for your presence and hope you have an enjoyable time. Thank you.
Thank you very much, President Kim. Professor Jung Sung-hoon is the director of Hanyang Institute of Energy and the Environment. He leads all the efforts behind this wonderful event today. Let's welcome Professor Jung for his opening message.
It is the world, universe we live in. It is said that there is a 7 times 10 to 22 stars in the universe. Yeah, a huge number. It is really wonderful, isn't it? There is also this look. Do you know him? Yes. Richard Smalley. He is the late Professor Richard Smalley. He won a Nobel Prize for his buckyball, and he was very popular. He was one of the most highly respected scientists working in the emergence field, nanotechnology, and he is well known for his scientific work. And he also presented a list entitled Top 10 Problems of Humanity for next 50 years. What we should pay attention to here is the first, second, and the fourth places on his list are the topics we want to cover this today. It is, It is energy and water and environment. Since the 26th United Nations Framework Convention on the Climate Change last year, the issue of reducing greenhouse gas emission has been attracting attention once again. In the line of the global trend, Hanyang University has created a new type of group research system that focuses on the energy and environment. This is the Hanyang University, Hanyang Institute for Energy and the Environment. Hanyang University is a leading innovation in university education and research through convergence between industry and university and between disciples in order to respond to changes in the international industrial order and nurture talents who will lead the solution to global environmental problems. Hanyang University, which pursues a practical academic tradition, has been recognized internationally for its excellence in engineering. Based on this dynamic, Hanyang University established the Hanyang Institute for Energy and the Environment as the institution that focuses its capabilities on three-dimensional problem solving and purpose-oriented convergence research and education. Celebrating the first anniversary of our institute, we are holding the first Hanyang Institute for Energy and the Environmental International Symposium with the theme of The Road to Net Zero, an energy and environmental perspective to leap forward as a researcher of international stature. As you can see on this slide, this symposium invited the world's best scholars in the field of energy and environment. I'm sure it will be a valuable time to exchange the latest knowledge and information to respond to ever-intensifying energy and environmental issues. So let's start the symposium now. Thank you.
Thank you very much, Professor Chung. Even though Professor Chung suggests us to start the symposium now, but we are doing too well. If you look at the schedule, we are quite ahead of our schedule. So shall we take group photos before we start the main program? I want to invite all the speakers and distinguished guests to the podium. Now we'll start the main program of the symposium. We have 4 speakers today, but each speaker is so heavyweight. We make one speaker, one session. So we'll have 4 sessions today, and each session has one presentation. Different moderators will read each session. Let me introduce the first moderator, and the rest of the moderators will be introduced by themselves at the beginning of each session. The first moderator is Professor Kim Sang-tae in Department of Nuclear Engineering at Hanyang University. Yes, Professor Kim.
Good morning. Thank you for the introduction and the opportunity to moderate this important session. Let me first introduce the first speaker of our symposium, Dr. Robert Stoner. Dr. Robert Stoner is the Deputy Director of Science and Technology at MIT Energy Initiative and also the founding director of the MIT Tata Center for Technology and Design. Dr. Stoner is a physicist by training. After receiving PhD in condensed matter physics from Brown, he moved on to build and manage successful technology firms in the semiconductor, IT, and optics industries. Notably, he served as the CEO of the Clinton Development Initiative and the director of the Clinton Climate Initiative for Africa, while living in India and Africa himself from 2007 and 2009. His present research includes the design and optimization of energy systems and business models in the developing world. Please welcome Dr. Stoner to the stage with big hands, please.
Is that better? Good. Thank you for your kind introduction. It's a pleasure to be here in such a beautiful venue and in such a beautiful country. I haven't been in Korea for many years, but I'm happy to say that this is the second coldest day I've experienced here. Last time it was even colder. But I grew up in Canada, where it's cold every day, and so I'm very comfortable. I am the Deputy Director of the MIT Energy Initiative for Science and Technology. That means that my job, and it's, I think, the best job at MIT, is to work with the entire faculty across the Institute on all aspects of energy technology development, energy science, energy policy, and energy economics. And we're involved in everything. Today, what I'm going to talk about relates to that mission. Whoops. And ultimately, what I would like to do is conclude with, my slides keep advancing automatically here, so I'm going to put this down. Some remarks about the proper role of universities around the world in the energy system and how we can collaborate. But first, I'll remind you about the international process we have for cooperation amongst countries to decarbonize the global economy. Then I'll talk about some of the technological pathways at our disposal, many of which we're working on at MIT, and many of which you're working on here at Hanyang University. And then finally, I'll talk about money, because money is ultimately what the process of converting the global energy system is all about. And then I will be able to return, having established that we need a lot of money, to the role of universities. And so you can hopefully guess my happy message at the end, which is that universities need to be much more at the center of how that money is spent. Now it won't advance. There we are. I went to the COP this year, COP 27 in Sharm el-Sheikh. And as you can see from some of these photographs, it wasn't the most exciting COP we've ever had. In fact, it was yet another step, I think, in a progression that began to take place just before the Paris COP toward letting go at the international level of the responsibility that I think the COP was taking for creating the mechanisms of decarbonizing the global economy, and instead retrenching to a more constrained role in which the COP is primarily a mechanism for establishing carbon emissions targets around the world and holding one another to task through frequent stock takings for achieving those targets. The idea, however, of the COP being the source of mechanisms, grand ideas like the CDM that were a critical component of the Kyoto Agreement that subsequently collapsed, I think has fallen away. This was much in evidence, in fact, both in Paris and especially in COP26, which we heard about in the introduction in Glasgow a year and a little bit ago, where it was very clear that the negotiators were stepping back from being the center of attention, and the private sector, project developers from around the world, bankers from around the world, were very much more at the center of activities and the center of the message of COP than they had been previously. Something else also happened at the COP that I think is important and that I'll build on in these remarks, and that is that small groups of countries began forming alliances, developing mechanisms outside the COP process and making commitments to one another that have been built upon over the ensuing year and will continue to be built upon going forward. And the particular commitment I'm thinking of is the one that was announced by the host country, the United Kingdom, as well as several other countries, including the United States, to work with the government of South Africa to develop a program for decarbonizing the South African economy that would be funded by those governments. This is called a Joint Energy Transition Plan, or a JET-P. And I think that they'll tell us something about how the future will unfold. I'm not sure whether I've advanced or what I've done. There we are. So just to get going, I'll point out, of course, that South Africa is a developing country, a country that has an energy system, but one that's highly carbon intensive and incomplete. Not everyone in South Africa has access to energy, and South African industry is somewhat starved for energy, as we read about frequently in the news. So this is a chart that sort of puts developing countries into the context of global emissions. It was produced by the IEA several years ago, the International Energy Agency, which produces many, many publications of this type and quality. And what it shows is oh, that doesn't work. Comparative emissions between 2017 and 2018 for the entire world of CO2. And you can see that between those 2 years, the first bar and the second bar, there's a significant increase, but it's not nearly as big as the increase could have been, as shown in the darker blue bar, had it not been for the fact that we actually achieved things in the world at that time that caused us to diverge from this sort of business as usual path. We developed substantial energy efficiency around the world. We began deploying more nuclear power, displacing fossil power. We built more renewables, displacing still more fossil power. And we fuel switched away from coal, especially toward natural gas. All of those things had the effect of reducing that increase, and yet the increase was there. And the increase continues to grow year on year for a very good reason. The reason being that not only is the population of the developing world growing, but the wealth of developing countries is growing. The quality of life is improving. People are gaining access to technologies like air conditioning, like computing, like central heating that make our lives very comfortable and pleasant. And of course, they should continue to do so. And so in large part, the challenge before us is to help these countries to continue to develop economically, as developed countries do at the same time, but in a way that no longer contributes to further emissions around the world. This is sort of obvious, but it's helpful to be reminded of it, and very helpful, I find, to be able to sort of look at the situation in a modeling context, because that's what I and my staff spend our time doing. A tool that I like to use to do this was developed by a colleague of mine by the name of John Sturman at MIT, and it's called C-ROADS. Now this is a rapid climate simulation tool that you can download from the World Wide Web, and I would encourage you to do that. It takes about 5 minutes to learn how to use it, and you can sort of play around with different assumptions. In fact, John developed it as a tool for climate negotiators to be able to very quickly assess the importance of their propositions in the course of negotiating climate agreements. And so you find people actually using this at COP conferences. It divides the world up into 6 different regions. The United States, formerly the world's largest emitter, the European Union, other developed countries, and you can see what they are, starting with Australia here and including South Korea, and then less developed countries, China, India, and other developed countries that include Brazil and the countries of the Caribbean and many other countries as well. And the idea with C-ROADS is to estimate or consider the possibilities of when each of these regions will begin to stop increasing their emissions and begin to decrease their emissions, and at what rate they'll do that. And you can see how the program works here. In the lower box, the lower left-hand box, you have the ability to enter what you think those numbers might be in terms of emissions peaking year, the reduction beginning year, and the annual rate of decline of emissions in percent terms. There are also boxes for entering the rate at which you think you'll stop or slow deforestation, and the rate at which you might begin to afforest, that is, to increase forest cover. In the upper left is shown the emissions for each region, and the United States is shown in red, the EU shown in green, et cetera, with China in light blue, India in pink, and other developing countries in darker blue. What I'm showing here is the business as usual case. On the upper right is shown what happens to the temperature over the course of the present century. And in the lower right, what the ultimate temperature reached by the end of the century is, in this case about 3.6 degrees. So you can see from the graph what the situation is. Right now, we're in a regime in which China and other developing countries are the most important emitters. And so we can sit in conferences like this, and we can sit back at MIT and in the United States and talk about all the wonderful things we're going to do to reduce our emissions. But in the end, it will not prevent us from getting to these very high temperatures unless we bring with us the developing world. So that is largely what I'm going to be talking about. Now, we can improve this situation by making commitments of the sort that were made in Paris. And I'm sort of mimicking the Paris Accords in this choice of emissions peak years, emissions reduction years for each of the 6 regions, and associated rates. And you can see that what happens is that the United States and EU curves, as well as other developed countries, begin to decline. But we haven't really done very much in the developing world. We've done a little bit in China, but nothing was pledged by India, nor in other developing countries. And so the temperature continues to rise almost as much and gets to about 2.9 degrees in these simulations by the end of the century. We can improve on that by asking more of India and China so that their emissions might be expected to peak and then fall off. This is consistent with many of the initial nationally determined contributions that these countries pledged in the year following the Paris COP. However, as you can also see, the temperature doesn't really fall that much from what we previously had. We're still at about 2.4 degrees. If we're going to do anything like 2 degrees, countries have to get more ambitious. They have to begin reducing their emissions sooner and at a more aggressive rate. If they continue to do that, you eventually get to a point at which we can keep the temperature to something like 2 degrees. But what it requires is not only that the developed countries have effectively decarbonized fully by the middle of the century, but also that the large developing countries have peaked well before 2060, maybe as soon as 2040 or 50, and begun to rapidly decrease. And here I've assumed that the rate of decrease of emissions is 5% per year. That's a very, very challenging number to reach, but still sort of feasible. And I want you to sort of keep these curves in your mind if you can, because we'll return to them in one form or another over the course of the next half hour. But 2 degrees isn't really the right number. We hear 2 degrees, but we'd really rather have 1.5 degrees. 1.5 degrees is a special number because it's a number above which the temperature doesn't decline back down to where it was in this pre-industrial baseline. It continues to hover in that 2-degree range and rise. But if we can keep it in the 1.5-degree range, then many models show that the global temperature begins to decline over the ensuing centuries and return to something like the pre-industrial point. So that's an important goal to have. And so it begs the question, what would we have to do to get to 1.5 degrees? Well, we'd all have to stop emitting in developed countries pretty much now and get to net zero well before the middle of the century, something like 2040. And the large developing countries would have to peak in the 2020s and 2030s and begin declining very aggressively by the mid-2030s and be out of the carbon-producing game by 2050, 2060. And again, keep those numbers in mind. But we can do it. I mean, at least according to these models, which are generally pretty well calibrated and thought to be right. Something that isn't, I mean, those are such aggressive numbers that they're sort of discouraging. So let me not discourage you. Because something isn't included in these graphs that needs to be. Well, it is in a sense, because we have deforestation and afforestation. We can reduce deforestation and sequester more carbon from the atmosphere into the soil and biomatter, and we can grow trees and sequester still more. But what we can't do in these models, there isn't a third column for removing carbon from the air or ocean in order to facilitate the further absorption. And so you could imagine superimposed on the curves of the previous graph, negative emissions from developing those technologies and deploying them at very large scale. And again, keep that in mind as we go. This was a subject much discussed in the Working Group 1 report of the IPCC's AR6 about a year ago, maybe a little bit more than a year ago, in which they discussed the scientific basis for climate change, and they produce a lot of models. And it's a good document to read, but it's very long. I think Benjamin Sovacool was involved in one of the working groups as well for this report, and we'll have more to say about it. What I want to point out, though, is just a couple of very important features. In the left-hand panel, we're looking at carbon dioxide emissions globally under 5 different scenarios. The usual terrifying worst possible scenario in which we do not very much. And then in blue at the bottom, a much more ambitious scenario in which we adopt new technologies very quickly, but also clearly we adopt technologies that allow us to go to negative emissions at a very high rate by the middle of the century. And so that curve corresponds to something like 1.5 degrees of temperature rise. The curve above it corresponds to something like 2 degrees of temperature rise. But in both cases, a very significant amount of negative emissions have been established. We are pulling very large quantities of CO2 out of the atmosphere. Those are the curves that I want you to sort of superimpose in your mind on the ones I showed you on the previous slide. It can be done, but it can be done only with a very large investment in very expensive technologies. Other things that are shown here that I'll just point out are the panels on the right-hand side of the graph that refer to methane emissions in the upper right. And you can see that in the light blue scenario, the 1.5 degree scenario, those emissions have to be reduced by at least a factor of 2 relative to their rate today. Now, our natural tendency is to blame the fossil fuel companies for that methane because they've got methane leaking from pipelines. Well, it turns out that only a relatively small amount of that methane comes from pipeline leaks and production leaks, something like 20%. Much of it comes from biological sources, including the decomposition of biological matter, as well as livestock, for example. And so reducing that methane is a very large challenge that can't only be accomplished by improving our energy production practices. It must involve new technologies for removing methane that has been emitted already. So very challenging. Nitrous oxide, we have to at least keep at current levels. And I'll point out that in the lower right-hand panel, one unfortunate outcome of reducing our fossil emissions is that fewer aerosols are formed in the atmosphere. Aerosols have a beneficial climate effect in that they reflect incoming sunlight. And so this creates another driver or forcer of climate that has to be accounted for by removing still further amounts of methane, nitrous oxides, and and CO2 from the atmosphere. So how do we get rid of these emissions by changing our economy? Well, this is a lovely graph that was produced by an organization called Our World in Data that shows what the global CO2 equivalent emissions are. That is, the emissions of everything converted into CO2 from different parts of the economy. And you can see that most of that graph is red. The red section corresponds to emissions related to energy use, mostly caused by fuel consumption. But there are also obviously large sections that are attributable to agriculture, forestry, and land use, waste, which leads to emissions of all kinds of greenhouse gases, and industry, excluding the emissions in industry that come from fuel use, but are rather associated with the production of materials, the most obvious example of which is cement, the calcining of lime emitting CO2 directly. And so there are sources of CO2 that we have to deal with, perhaps through negative emissions, perhaps by developing new technologies, in addition to those we have to mitigate within the energy sector. But within the energy sector, which comprises 75% of these emissions, almost, it's helpful to break it down into the three major components. And the first of those is energy use in industry. And you can see in this piece of pie that runs from about 12 o'clock to about 3 o'clock that there are all kinds of sources of industrial emissions that have to be mitigated. Some of those can be mitigated by capturing CO2 from flue stacks. Others will have to be mitigated in other ways because they're produced in the course of producing the chemicals, which consume fossil fuels as feedstocks as well as sources of energy and produce emissions. Changing those is extremely hard. It's also challenging to reduce emissions from energy because of the very wide variety and scales of industrial processes. So very challenging. The second major piece, I wonder how I can control this a little bit, is emissions from transportation. Not quite as big as the industrial emission sources. And much of those are from road transportation. We also have aviation and shipping. The road transportation is by far the largest piece. Now, we've made great progress here by electrifying automobiles, beginning to electrify automobiles, and I believe that will begin to take off. It already has taken off very, very rapidly over the next several decades. And we will see that piece of pie shrink dramatically, provided that the electricity that's being fed into those electric cars is produced renewably. The aviation and shipping pieces will be much harder to contend with. Aviation requires very energy-dense fuels, and it's hard to find such fuels that are not hydrocarbons. There are certainly efforts to do that. There are even efforts to electrify aviation, but it will require, I think, great thinking, and it may even require the continued use of fossil fuels or the preferential allocation of biofuels as liquid fuels for aviation. Biofuels, of course, have the wonderful property of, at least in part, cycling CO2 or cycling carbon in the atmosphere, and so are more carbon neutral than fossil fuels. Shipping is not quite as challenging as aviation, but still very challenging because it requires energy density as well in order to not displace too much of the cargo space, which after all is the point of shipping. But alternative fuels are already being investigated. For example, ammonia, which we'll say something more about, as a source of hydrogen or as a fuel itself, provided that its associated N2O emissions can be captured and in some way sequestered or converted to a safer form. And so I'm feeling pretty good about the transportation sector. The last of the three major sections is buildings. Not the embedded energy or not the embedded emissions in buildings, but rather the energy use in buildings, especially energy use for heating and cooling. Cooling is a very rapidly growing part of global energy consumption, partly because we're getting warmer, but partly because it's being increasingly adopted in poorer countries that are also tropical. India, of course, is an important example of such countries, as well as parts of China. This is a very difficult problem to deal with as well, but with more efficient air conditioning and the use of renewable electricity, we can also dramatically shrink this piece over time. In the Northern Hemisphere, where we're using fuels to heat spaces, we need to convert that heating to electrical means, along with producing more low-carbon electricity. And of course, one of the most important technologies that is gaining very rapid adoption is high-efficiency heat pumps. And so we'll see more of those things. And you can begin to imagine, just scanning across those three major slices, that we could substantially reduce the energy from those three major sectors. And that's what we're trying to do at MIT. This slide is not showing up properly, so there's a lower piece missing that I'll describe to you. We have increasingly shifted our emphasis within the MIT Energy Initiative from what was originally an emphasis on technology discovery, increasingly toward technology development and advancement and translation to commercial practice, and more recently, strongly toward modeling and analysis. Because the world is moving in the direction of implementation and deployment, and efficient implementation and deployment depends on having a quantitative understanding of how low-carbon energy systems go together. We have to do this efficiently in order to make proper use of capital and keep the costs of renewable energy competitive with those of our present energy system, or it won't happen. So we have developed complex models of all parts of the economy, all parts of the energy system that look both at supply and demand. And we've reinforced that work by developing work streams within MIT that are focused on those three energy end-use sectors: industrial processes, use in buildings, and transportation, which I've just described. And then three core strategic approaches for dealing with them. The first is managing emissions. That means capturing CO2, reducing leaks, etc. The second is clean power production and the electrification of loads that are not now electrified, EVs being an obvious example. And third, the development of low-carbon fuels, fuels that can take the place of fossil fuels in applications where fossil fuels are very hard to replace. I'm showing them in a matrix like this because these three strategies and the three major end-use sectors all interact with one another. You can't attack and decarbonize any one of them in isolation from the others. For example, with hydrogen, we talk about hydrogen as a possible source of fuel for cars. But to produce that hydrogen requires storing the gas or a liquid when cars are not being used and when you need an excess, or deploying it more economically in other applications that can consume hydrogen. For example, industrial processes or transportation. And so the cost of carbon depends on those compatible uses and establishing as much as possible level consumption over time in order to minimize storage and get the best possible agreement between the rate of production and the rate of consumption. And similar sorts of intersections and so-called sectoral overlaps or sectoral interactions arise amongst all of these strategies and end-use sectors. So modeling is very important. I'll just speak briefly about some of the technologies and pathways that we're focusing on, and that I'm sure you're focusing on as well, that will become part of every country's future energy system. But I think it's very important to understand that will happen in a different way in every country, depending on the availability of renewable resources, depending on the nature of load, depending on the existing fuel system and energy system that has to be replaced. I guess that's all obvious. And you may be thinking, well, that's obvious. Why is he bothering to say this? I'm saying it because it's perhaps not obvious that that's a dramatic shift in the nature of the energy industry relative to where we're starting. The present energy system is based on the idea of producing energy in the form of various fossil fuels at a relatively finite number of point sources, oil wells, gas wells, mines, and then distributing them in an outward manner to all of the countries in the world, where they're consumed in, although in different proportions, in almost exactly the same ways. We have coal plants in the United States that are indistinguishable from coal plants in South Korea. They have oil and gas plants in Russia that are indistinguishable from oil and gas plants in South Africa. We're going to a regime in which energy will now be produced locally at an enormous number of sites, in an enormous number of ways, and consumed within those economies. And that means that no longer are we in this sort of broadcast distribution regime, but rather in a regime where we have to think very carefully about the integration of load and supply and the connective tissue, the pipelines, the wires that bring energy to industrial facilities and homes and transportation centers and return effluent to places where it can be disposed of. And I'm thinking primarily of CO2 as the effluent, of course. To make that happen efficiently, requires an integrated approach to supply and consumption that I think might lead to a very different sort of future energy industry than the one we have now. Large companies like Shell and Exxon, for example, will have to move away from this sort of present system of point source production and distribution to one in which they're much more engaged with the low carbon production of energy and the connective infrastructure, as well as the novel processes, especially industrial processes, for consuming that energy, which always involves integration and cross-sectoral interactions between different industries and parts of the economy. So this is a challenging aspect of the energy transition, and again, one that requires modeling in order to get the efficiencies that we require. It will not be an ad hoc sort of development process. So just looking at these technologies now very quickly, again, we have our three basic strategies: emissions management, that is capturing on the left-hand side CO2 from either power generation or fuel and chemical production, from cement, steel, and non-ferrous metal production, and other industries, as well as transportation, which means that we'll have to have various ways of capturing emissions and different technologies in each case. The technologies for capturing flue stack emissions are still somewhat primitive. We use amines to do that, and chemical looping. There are electrochemical approaches that I think are very promising, and the use of novel membranes for enabling capture of CO2 that can be more energy efficient and more robust in flue stack conditions. Tailpipe emissions, direct air capture, that is pulling CO2 out of the air, which involves right now approaches that are based either on the same amine technologies that we use in flue stack capture or even more energy expensive cryogenic processes, all of which with air capture require the movement of enormous amounts of air through enormous machines, because having escaped either the tailpipes or flue stacks where they're being conveyed to the atmosphere, they're now much more diffuse. And so I don't want to give you the impression, by even showing direct air and direct ocean capture of CO2 on these charts, that this is an easy solution or an affordable solution or even a feasible solution from an economic perspective, but it may be one that we need and where we have to pay a penalty economically in order to contend with our excess emissions. And so these are challenging but very much worth developing technologies where we're expending a considerable amount of resources at MIT. And then, of course, we also have to deal with leaks and unintended reactions of released chemicals into the atmosphere, including, by the way, hydrogen and ammonia, two non-greenhouse gases that, however, have been shown in fairly recent studies to have the potential to be converted in the atmosphere through a series of steps into greenhouse gases. And so two of our great saviors, ammonia and hydrogen, still have the potential to cause us climate problems if they leak uncontrollably. So developing leak controls for those gases as we begin to get into them, and we will, is crucially important. And then finally, N2O and NOx, which are produced from tailpipe emissions and other sources, flue stacks, as well as from the conversion of ammonia in the atmosphere through ammonia radicals into oxidized ammonia, or oxidized nitrogen. In clean power and electrification, of course, we're working on a large number of generation and network strategies, and a couple that I'll point out here that I think are especially interesting are a return to geothermal power, taking advantage of two major developments over the last decade or so. And that is, one, the ability to do horizontal directional drilling at great depth. And in the other case, the ability to drill uncased wells deep into the ground. And I'm talking 10 to 15 miles in order to access high quality heat. And so we have the ability suddenly that we did not have the last time geothermal became an important technology to make geothermal wells and heat exchangers at great depth that can be used to source low carbon energy and produce electricity essentially anywhere, in the parking lot, for example, of Hanyang University. The second I'll point out is fusion. If you read the newspaper, and I'm sure we all do, you will have noticed an important, and I think it really was an important announcement made by the Department of Energy in the United States just the other day, and that is that an energy positive nuclear fusion reaction was achieved. I was a little bit appalled by this announcement because it not only implied, but directly stated that this was therefore a harbinger of future vast quantities of zero carbon electricity. It's not so. This is a technology that was primarily developed for nuclear weapons testing. I was involved in that technology, and in fact, my group designed the beam lines and beam steering systems for the National Ignition Facility. And so nuclear fusion was certainly demonstrated, but not in a manner that I think is very likely to lead to an important commercial result. However, there are many nuclear technologies using DT reactions, as this system does, but this is an inertial confinement system. Rather, nuclear fusion reactors based on magnetic confinement using conventional tokamak designs, as well as other inertial systems and other tokamak systems that I think really are commercially exciting. One of those is Commonwealth Fusion Systems, which is a Massachusetts company, but that's one of several dozen nuclear fusion startups around the world now who are racing to get to a practical commercial fusion reactor within the decade. We think our fusion system has the possibility of producing, as the National Ignition Facility did, an energy positive fusion reaction within perhaps as little as 3 years, and a functioning electrical generating fusion station before the end of the decade. Now, that doesn't mean we're saved at the end of the decade, because it's not at all clear that that system will be commercially viable. It will have reliability problems, for sure. It will have lifetime problems. It will have uptime problems. It will be very expensive. But we'll then be on a path to develop fusion reactors at commercial scale in quantities of tens of thousands that may be commercially viable. But the journey is long, and we're at the beginning of it. But I think that within the lifetime, certainly of people in this room, we may very well have substantial fusion reactors and the ability to generate copious quantities of low carbon energy. I hope that our political leaders and nuclear industry, who will almost certainly be involved in the new fusion industry that arises, will have the wisdom to guide public opinion and to nurture public opinion along the way so that the unfortunate circumstances that have occurred with the fission nuclear industry don't repeat themselves and bring this new industry to a premature end. Let me continue. Clearly, I talked about demand in the previous slide and the need to electrify load, which I believe is rapidly increasing. And we'll see a lot of decarbonization as a result of the strategy. And then finally, low carbon fuels, the development of biofuels, electrofuels, solar fuels, and hydrogen by various routes, as well as ammonia, both as a fuel and carrier. We study biofuels a lot because they're a convenient, at-hand approach to having fuels at reasonable quantities that can be used in hard to decarbonize or hard to defuelize applications. However, I want to point out, biofuels are limited. We only have a certain quantity of these materials that can be produced, and so we have to be judicious about the applications into which they go and efficient in their production. And then there are, of course, a lot of other things that can be done that are connected with energy throughout the economy, I think the most important of which relate to land use. Not only reduce deforestation and afforestation, but peatland preservation, coastal management, the development of mangroves and so on, and reduced agricultural waste. These are very important issues, and I'm embarrassed to say issues that we don't pay enough attention to at my engineering school. I hope you do at yours. Because there are too many engineers and maybe not enough biologists and environmental scientists. I think this is and hopefully we'll hear more about this morning. This is a tremendously important area for focus. So let me just briefly talk before moving into my concluding remarks about how these things can come together, and let me do it in the context of a particular country, Indonesia. Indonesia is important because it has relatively low emissions now for its size and population. But because of the growth of its economy, it has the potential to become one of the world's largest emitters, perhaps the world's fourth largest emitter, very quickly. But as it stands now, and this is shown nicely in this study by the IEA that was released just in September, its economy is largely, or the emissions in its economy come largely from agricultural emissions. So this chart on the lower left shows for the period between 2000 and about 2020, the emissions from all sources. In pink, we're looking at the emissions from energy. And you can see that that's fairly small. It's something like no more than a half and between a quarter and a third in a typical year, whereas the vast majority of emissions are coming from agriculture and waste. So we have the possibility here of separating these problems and approaching them both with great intention. And I would point out that all of the green things, the agricultural things, are very much within the control of the government of Indonesia. These are policy decisions. They're not easy policy decisions. They're political decisions that affect large numbers of people, large swathes of the economy. But there are very, very positive signs in Indonesia that they're moving in the direction of getting control of their excessive agricultural emissions. They have outlawed the further development of peat bogs, for example, for growing palm oil. I'll come back to how that has affected, their engagement in that has affected the willingness of outside countries to become part of the transformation of their energy system, where outsiders really can make a difference by providing capital. If we look just at that energy segment, the pink segment, you can see what could happen in the future. So the lower left-hand panel here shows, starting about 10 years ago through mid-century, two trajectories. The dotted one is the so-called stated energy policy scenario created by the IEA, which shows how the present-day emissions continue to increase and don't peak until sort of mid-2040s, and then slowly decline as they begin to adopt at an economic pace low-carbon technologies. The lovely colorful curves below that show what could happen if they make aggressive moves through policy to reduce sectoral emissions, that is, emissions from buildings, transportation, and industry. Now, I only showed 3 end-use sectors, those 3. The IEA tends to show 4, electricity being the 4th. I don't, because electricity is not a final end use. Electricity is actually a transformational step. and end use is in the buildings, transportation, and industry. But they break it out here. But you could imagine that being sort of evenly spread across the three sectors in principle. The important point is that they were able to reduce emissions from electricity by about 2050, basically to zero. And to make some progress in reducing emissions from the rest of the economy. And by 2060, to have reduced their emissions by roughly a factor of 8 overall from energy. That's going to take a lot of money and a lot of know-how and a lot of commitment and policy. But the point is that it's sort of achievable in the scenarios that the IEA investigated. And there are many such scenarios that could have been investigated. There's not only one path, but this is a path. And you can see the detail of how that's accomplished on the right-hand side. The only important thing that you have to see here is that essentially by 2060, emissions from buildings, starting on the right, transport, industry, other transformational processes, and electricity basically all go to zero. In fact, in electricity, they go below zero. In other words, within the electricity sector, they're using technologies that remove net CO2 from the atmosphere. And that probably means bioenergy with carbon capture and sequestration, growing trees, burning the trees to produce electricity, and capturing the CO emissions in the flue stacks of the plants in which that takes place. So doable. All right, so that's a big developing country. And money needs to flow into that developing country, and that's a challenge. We're attacking this problem in the United States, which is a rich country, where money doesn't have to flow in from anywhere. It exists. There just needs to be a political commitment to spend it, to do these things. And finally, after many, many years this year, we've had that political commitment to actually do something with the passage of two very important acts. The first is the Infrastructure Investment Act, which came first, which invests roughly $500 billion over 5 years in infrastructure, which is largely infrastructure to demonstrate and further develop a number of important low-carbon technologies. And I'll say that strategically, the act is formulated with a very deliberate intention to develop hydrogen as a critical fuel for the future. Along with that, it develops carbon capture and sequestration. Now, the reason in the United States those two things go together is that we are blessed or cursed, depending on your point of view, with a very large amount of natural gas. And the lowest cost pathway today, in some parts of the country at any rate, to producing hydrogen is to separate hydrogen from methane, having produced the natural gas, and then sequester that CO2 produced underground, or use it in other applications. And so the act is formulated to subsidize the production of very large autothermal reforming and steam methane reforming facilities where hydrogen will be produced along with CO2, and carbon capture and sequestration facilities under the Gulf of Mexico and in other geological formations around the country. And this can lead to some substantial hydrogen production. It also anticipates that some hydrogen will be produced by renewable electricity and hydrolysis, and perhaps other emerging technologies, and it provides for subsidies for that infrastructure as well. It also subsidizes a national EV charging system and the design of carbon capture facilities for existing and new industrial facilities. And so this is a big press that works in an integrated way to make these technologies feasible and economic, and thereby to help create a market for hydrogen, which will induce private investors to begin building facilities that consume it. The second act, the Inflation Reduction Act, which was passed just this fall, uses subsidies through our taxation system primarily to reduce the cost of that produced hydrogen and produced renewable electricity by literally paying people to produce it, which makes the production of hydrogen even cheaper and inducing further investment in the industries and technologies that consume hydrogen and other low-carbon energy carriers. So these two acts together, along with a third called the CHIPS and Science Act, which doubles spending on US science over the next decade. Think about that. That's through the national labs as well as universities. Come together to deploy roughly $1 trillion between 5 and 10 years to decarbonize the US economy. There's an assumption that in the ensuing 10 years, there may be continued subsidies, particularly in the production of these low carbon commodities. But there's also an assumption that private investment and private innovation will have reduced the cost so much that adoption will continue apace until the US energy system is essentially fully decarbonized by 2040 or so. That would mean that something like $20 trillion would have been spent. And maybe between $1 and $2 trillion would have been contributed by the United States taxpayers in the form of concessional money to industry to make it all happen. So roughly 10%. And that's the way the subsidies are constructed and calculated. There's a presumption that there's gearing between that public investment and private investment of about a factor of 10. I'll also point out that the $20 trillion that's going to be spent between those subsidies and private sector investments is about the same as the GDP of the United States, the gross domestic product. And it turns out that if you scan around the world, and this is, if you learn nothing else from this discussion, remember this, the cost of building or replacing your energy system is about 1 GDP, no matter what country you're in. And that provides a very, very useful scale for calculating how much private and public investment has to take place in order to facilitate the transformation country to country, region to region. And it tells us something more. We're doing something good here, I think. We're decarbonizing an important emitter. We're developing a lot of technology, but we're also doing something bad. We're making it hard for countries that can't afford to do this to do it themselves. I sat across the table with a group of executives from Ecopetrol recently. Ecopetrol is the national oil company of Colombia. And we were talking about their options. And I said, well, why don't you use your abundant solar energy and fresh water to produce green hydrogen? And they said, well, that's a fantastic idea. However, those guys on the other side of the Gulf of Mexico in Houston are going to be doing exactly the same thing, and the US government is going to be paying them $3 a kilogram for the hydrogen that they're producing. We can't compete. We can't go into that business unless somebody gives us those subsidies too. And we're a poor country, and we can't afford to borrow money the way the US can. We don't have the luxury of printing money the way the US can to be able to produce the subsidy money ourselves. We have to bring it in externally. So that's a way of introducing the topic of just how much money would have to come from outside developing countries to allow them to develop clean as well. Now, there was a lovely paper written for COP27 by my friends Nick Stern and Vera Songway, who are both economists, and they tried to put some numbers to these things in a very sophisticated way, and there are lovely appendices to this report that show you how to do it right, but you can also do it with my GDP method. But they point out that $1 trillion a year in external finance has to be mobilized by rich countries in developing countries in order to allow them to proceed. Now, I could have told them this without their fancy appendices by looking at the countries in the world that have government bond ratings below AA-. That is, they're below investment grade, so they can't raise the money to subsidize themselves through bond issuance. It turns out that the GDP of those countries combined is about $60 trillion. So if they're going to fully decarbonize themselves in, say, 50 years, it's going to take $1 trillion a year. It might take a little bit more than that if they go faster. And of course, there's the possibility that my one-to-one relationship between GDP and energy system is perhaps a little bit off. But that's the reason for that $1 trillion. Now, I've copied verbatim the summary statement that this report makes that summarizes a number of points that I think are very important. One is we really need to accelerate this project development in these countries. We've got to build those electricity generating stations. We've got to build that infrastructure to carry low-carbon energy from sites of production to points of consumption, and at a very large scale. And that means we have to do a couple of things. We have to mobilize mostly private money. This is a restatement of what I said in relation to the gearing that was assumed in the IIA and IRA. There's an assumption there of a 10-to-1 private to public investment ratio. And that means that in developing countries just as well, there has to be that same sort of 10-to-1. So $100 billion of that $1 trillion has to be basically free money into these countries. And so they return to that point in a way in these lower points, noting that there has to be a doubling of concessional finance. There's already a lot of concessional finance in the world. It's deployed by the multilateral development banks, the World Bank, the Asia Development Bank, for example, that sends money into developing countries to help them develop. That amount of money is between $150 and $200 billion a year. The $100 billion that's required to subsidize or enable this $1 trillion investment would effectively double that official development aid volume. And so that's, again, a helpful scale. In order to help the developing world decarbonize, we have to more or less double ODA. That's not that bad. $180 or $200 billion between all of the developing countries in the world every year is a feasible number. 250 or 280 in relation to the incomes of, or GDPs of those countries is the same number. So very doable, and yet we're not doing it. But we can. The harder part is actually the private money. It's not like people are lining up in South Africa to help the South Africans enact their Jet P, which I referred to earlier in relation to Glasgow. There are a lot of reasons not to do that. These are risky countries to invest large amounts of capital in. The governments have poor records of paying lenders back in some cases. And so you have to get very willing money and at very low rates of interest. Those are sort of incompatible concepts. But one very good idea has been advanced by the president of Barbados, Mia Mottley, in what's called the Bridgetown Initiative. And you might have read about this in the papers as well around the time of COP28 or 27. The Bridgetown Initiative proposes the use of something called special drawing rights to create a pool of capital, low-cost capital, that developing country project developers, private project developers can draw on to build low-carbon energy projects. And I'd be happy to talk about it more in the Q&A, but the essential point is that special drawing rights are an existing mechanism that create liquidity for countries around the world that are created by the International Monetary Fund every year in proportion to each nation's GDP. And they're held by the IMF and made available to those countries so that they can borrow money in times when they need liquidity in order to effect international transfers and transactions. Fine. Well, it turns out that the rich countries to whom those special drawing rights are being issued don't use them. They can raise capital for international transactions in other ways. They can issue bonds, they can print currencies at a lower cost. And so they sit there. So Mia Mottley has proposed to make those special drawing rights available to the tune of between $500 and $600 billion a year using the unused portion. That's half of the $1 trillion we think we need. So again, a very feasible number, along with the concessionary portion. And I think these two things are rather exciting. So let me begin to wrap up by talking about what now has happened to organize those funds and deploy them in developing countries. I mentioned very briefly the initiative led by the UK with respect to South Africa at the beginning of this lecture. And that is called the Joint Energy Transition Plan, or JET-P process for South Africa. It was announced in Glasgow and developed over the course of the year between then and Sharm el-Sheikh. And we had an update in Sharm el-Sheikh on what's happened. And essentially this: the South Africans have decided that they're going to deploy about $98 billion, say $100 billion a year over 5 years in their energy transformation. The developed countries that are part of a so-called international partner group led by the UK are going to contribute $8.5 billion to that pool. Well, look, that's 10%. So we've got the right gearing here. Concessional money coming into this process to make the transformation happen. The rest will have to come from private sources and perhaps philanthropy, but we'll talk about that in a moment. The point is that this is the right scale of concessionary money, the right fraction of concessionary money, and the volume that's contemplated by South Africa of $100 billion over 5 years, if you think about it as a 20-year program, or $400 billion in total over 20 years, is exactly the same as their GDP. So it's the right scale too. So this is a meaningful and sensible plan. The second country that has begun to get into this process is Indonesia, which is why I showed Indonesia's possible futures. They were selected by the International Partner Group in this case because of the importance or rather the opportunity to decarbonize the power system, the energy system there, using external money. And again, they have developed a program that is appropriate in terms of the scale of concessionary money and overall size of capital spending that will be deployed. So these are the first of many JET-Ps that we'll be seeing over the next several years, and I would encourage you, all of us, to keep an eye on those as they develop and see if we begin to approach this trillion-dollar figure. Let me wrap up by saying something about philanthropy. Philanthropy is often cited as a third arm that could be brought to bear in these situations to close these multi-hundred-billion-dollar gaps. Let me just say it can't be. Total philanthropy now devoted to climate change mitigation is about $10 billion a year. That's effectively 0 or 1% on the scale of the total amount of money that has to be deployed. But there are good things that philanthropic organizations are doing, and I've been involved with several. One is the Global Commission to End Energy Poverty, which has established expert advisory committees led by universities to advise governments on their electricity and energy access programs, a very cheap way of bringing real expertise to bear in these processes. And the second, and more important, I think, is the Global Energy Alliance for People and Planet, both of them launched by the Rockefeller Foundation. The Global Alliance has mobilized about $1.5 billion, a significant fraction of the total philanthropic funding available in the world, to bring expert teams together to negotiate on behalf of developing countries with international partner organizations. So this helps us to see what the role of not only philanthropy can be in the future, but the role of universities. So let me wrap up by sort of restating my two major points and then making a third pitch to you. And the first is that the rich world really has to step up with this $30 to $50 trillion commitment beginning now in order to decarbonize the developing world. There is no alternative. The money has to be there, and it won't come from other places. The second is that philanthropic funding shouldn't be wasted in trying to subsidize that $30 to $50 trillion commitment, but rather should be used to fund expert pools of people who can come and sit on the same side of the table as developing countries and help them to find their paths. And so my pitch to you, as members of the world's university system, is that we have a role in that process to be those experts. This is something that we've begun to formulate formally at MIT, and which I hope we can talk about more, the idea of creating what I'm calling a low-carbon university co-design institute that operates on, I think, organizational principles that everyone will be able to understand, that gets us into the game and gets us into the game with a sense of urgency. So let me leave it at that, and thank you all very much.
Thank you for the wonderful overview of net zero plans and what's required for us, as well as the rich and developing countries to do. Now, let me take questions from the audience. Okay, yep.
Thank you, Robert, for the great presentation. I am Min Sub-song from Department of Nuclear Engineering, and living in Seoul, I already thinking about that we are living in a very efficient city. You know, there are more than 10 million people in this city. So I was thinking that promoting the urbanization or the motivating the modern city to the people could increase the energy efficiency of the nation. So what do you think about the urbanization of the countries for the developed countries?
There's no, thank you very much. The question is, what about the role of urbanization in developing countries? It's very important. It's clearly occurring. It has already substantially occurred in developed countries, and I believe that developing countries will mimic that process. I've been very impressed by the public transportation that I've seen in Korea as well. Clearly, there's an opportunity to develop cities differently in the developing world, to take advantage of modern thinking about efficiency in transportation, efficiency in buildings, and to live differently, but not necessarily worse. So thank you very much. That's a very good question.
Thank you.
Yeah, my name is Dongwon from School of International Studies. I want to ask you especially the one question. You explained the Infrastructure Investment Act of the United States, especially the hydrogen. The hydrogen is very important here for Korea, especially for the iron and steel industry and power and transport. So does the United States have any target for the production cost of green hydrogen in case of the Infrastructure Investment Act?
Yes, let me see if I can remember what it is. Yeah, right, the 111, the $1 per kilogram in 1 decade is the plan. So that's where we are. Now the subsidy that's available under the IRA is $3 per kilogram right now, to give you a sense. So we're a long way from there. But the idea with that $3 for the right kind of hydrogen is to get you into a regime where industry can see what the future is and build accordingly. Thank you for that.
Okay, there's another question over there.
Thank you, Dr. Stoner, for your excellent speech today. And I'm Jin-soo Kim at Department of Earth Resources and Environmental Engineering here at Hanyang. Also, thank you being here despite this cold weather. And I'm a little curious about the most coldest experience in Korea, because you mentioned this is the second coldest. I'm doing some research with Benjamin here for the industrial decarbonization around the world by industry, such as iron and steel and chemicals and refining, etc. In the research, I'm always thinking of the role of the nuclear energy for our carbon neutral pathway. Yes, I totally agree with that. The nuclear will play a substantial role for the decarbonization, but there is some debates on the nuclear energy because of the externalities and external costs, including the nuclear waste. Maybe EU taxonomy or Korean taxonomy is an example of that kind of debate. Could you give us more details or a kind of opinion for the what options we have with the nuclear energy in the future for the decarbonized world?
Well, it's a very important question. I'm not sure I can give you a great answer because I'm not a nuclear engineer. I think most of my expertise comes from the fact that I live nearby a nuclear power plant. And I've had some involvement with the Nuclear Regulatory Commission in the United States as a citizen, sitting in meetings in which what I've observed is that when nuclear power plant operators come in to present and request license extensions, members of the Nuclear Regulatory Commission will come in and sit with them on their side of the aisle while the public sits on the other side of the aisle. And they laugh and they joke and they smile throughout those hearings as the public makes comments and expresses their reservations. And it's a reminder that we have a very unhealthy relationship between our nuclear industry and the public, despite the fact that we have an enormously successful record of operating our nuclear fleet. My further observation from hearings related to the now decommissioning of the nuclear power plant that I can see from my house if I crane my neck is that that unhealthy relationship continues. Our plant is now being emptied of its spent fuel. And rather than disposing of that spent fuel in the way that makes me feel comfortable, like by taking it to some place far, far away and burying it, they're taking it outside and they're putting in concrete casks in the parking lot where they propose to leave it for the next 1,000 years. And when you raise this as somewhat disconcerting, the reaction of them and the Nuclear Regulatory Commission is that you must be insane. And again, a very unhealthy relationship continues to be fed by this sort of really very bad thinking. And the third point that I would make with respect to this sort of relationship is that we now are in a position where we need to dump something like 100 million liters of treated water from the spent fuel pool of this facility, or get rid of it in some way. And again, I would like to see it trucked off and put somewhere else. The proposal is to dump it instead into the small bay on which it's located, called Plymouth, Massachusetts, where the Pilgrims arrived, who first settled that part of the country 400 years ago. It may be that that's a fine thing to do from a health perspective, that doesn't make the water radioactive. But what was obvious to the people of the town is that it makes the town radioactive as far as the tourists and consumers of fish that are produced there are concerned, and would have a tremendous negative effect on the local economy. That was not being taken account of in the arguments that the industry was making to take this course. And furthermore, they lied about their intentions and were caught and so on. The point being, I think, could get by without nuclear power in a future energy system, but it would make that system much more expensive, much less reliable, and very concerning as a result. My greatest concern is that we have this negative relationship and will continue to have the negative relationship, not only in the United States, but elsewhere, between the industry and civil society. And for some reason, we're not fixing it, but we have to. So that is, I think, the sad state of the nuclear power industry around the world. And I gather that in South Korea, we have a similar sort of relationship and concern. And I think there's probably, as we were saying in our previous meeting, much to learn from one another about best practice in order to heal that relationship and make further progress.
Wonderful. Since the time is pressing, let me end the first session here. And first, let's thank our speaker. And we'll begin the next session in 5 minutes. So we will begin at 11:03 after taking a 3-minute rest. Thank you.
All right, let's get started with our second speaker here. I am very happy to introduce Dr. Bruce Logan. Dr. Logan is an energy and environmental engineer serving as the Kepi Professor of Environmental Engineering and the Evan Pugh University Professor in Engineering at the Pennsylvania State University. He is also the Director of PSU Energy and Environmental Institute and also Hydrogen Energy Center at PSU. He is one of the HCRs from Clarivate for 8 consecutive years since its beginning. And his current Google H index reached up to 168.
He has always been an inspiring researcher to all of us. Bruce, it's all yours now. 1 hour.
That very nice introduction, and I really like to say I'm very pleased to be here today. Thanks for the kind invitation, and thanks to Dr. Stoner for actually introducing many things that I'll also be discussing, but I'll probably be looking at it from a slightly different perspective, which I think is good. First, let me tell you where I'm from here. Maybe you don't know where Pennsylvania is, but it's by that big star up there. Oh, this is going to be one of those. It's by the big red star up there. That's where Pennsylvania is. And Penn State is in the middle of the state. It's about roughly halfway between Pittsburgh and New York. It's roughly halfway between Pittsburgh and Philadelphia. We like to think of it as in the middle of everything, but next to nothing. It's centrally isolated, so a small town, shall we say. This is a graph that you've seen today in various forms. It's showing really the prediction of global CO2 emissions, but this is also the challenge for many of the students in this room. This is the challenge of your generation. You enter into this environment where we either get a cap on carbon emissions and greenhouse gases, or temperatures continue to rise. And one thing that people sometimes don't focus on enough is that when the 2 or 3 or 4 degrees C number is mentioned, that's global average. Land temperatures are about 60% higher. And of course, due to climate disruption, on any given period of time, there are days or even weeks when temperatures can be significantly above average or below average. And so this is a future that we want to avoid, where we continue to have these increasing emissions. And so how are we going to do that? Thesis that the energy infrastructure and addressing climate change is about building, exerting a strong enough force to change the momentum of the direction we're going. Now, to achieve changing that momentum, what we have to do is find out how we can educate essentially 8 billion people today, or 9 billion or 10 billion in the coming years, because if we're going to affect that change, we need the momentum of all these people to create this change. Well, what's momentum? It's fitting that the previous speaker was a physicist, because if you look at mass and acceleration, that's force, and force is needed to change the momentum, which is mass times velocity. But that's not really what I want to talk about here today. I want to use it in terms of its more common use, which is the impetus and driving force for the development that changes the course of events. We want to change the current momentum of furthering an energy infrastructure based on fossil fuels by exerting sufficient force. And we can do that through people. We can do that through policy, which is a deliberate set of guidelines to achieve this, and of course, through people. And hopefully not increase the number of people past the predicted 9 or 10 billion on the planet. It's very clear that there's a need to change this. We can see it in really the young generation who are going to live through a time of climate change. They're sad, they're afraid, they're anxious, they're angry, and they feel somewhat powerless. And yet, I think everybody in this room, you wouldn't be here if you weren't also a little concerned, but also more concerned about creating change to achieve this situation. And yet, not everybody's on board with this. One of the things we suffer from in the US is that roughly a quarter or a third of people sort of oppose making changes. It's not whether they believe in it or not, it's just they don't want to do it. So we have to kind of create a situation where there's a desire by everyone really to make this change, or it doesn't sufficiently happen. In fact, we see these bills passed in the US which would outlaw using clean energy. I mean, this is all in the wrong direction. So we look to policy to make these changes, and we've had COP26, COP27, and the previous policy meetings and government meetings, and now businesses, to try and move the direction. But who really controls this? Well, if it's policy and it's these conferences, we haven't been very successful in that. If you look at the 4 meetings prior to COP27, the main ones with those little red arrows, you can see that atmospheric CO2 continues to go up in sort of oblivious to those conferences. And global CO2 emissions, they have this kind of jagged increase, but an increase nonetheless. And so we need to find some way to change the momentum, the direction we're going in order to address this. Now, some people say, well, if enough wildfires or enough flooding or enough disasters occur, surely that will change people's minds. But we've had all sorts of global disasters. We've had oil crises. We've had the dissolution of the USSR, financial disruptions, COVID. And each time, what history tells us is that we resume going back to the normal way of life as quickly as we can. So the direction doesn't really change unless we can change the momentum and the direction that we're moving in. So what I want to do today is get you to think about how your activities and your life plays a role in this as a way of talking to other people about how we might change things. And I think the key to education here is to get away from these really big, powerless numbers like gigatons and exajoules and quadrillion BTUs, and get down to numbers we can understand. That way we can start to say how much energy we're using. Is turning off a light bulb enough? Is taking the metro or the subway instead of driving my car enough? What is it that I do every day that can help change things as the consumer? And then, how do we deal with other greenhouse gases? So first, Lord Kelvin said this. He said, when you can measure what you are speaking about and express it in numbers, you know something about it. Well, I think we know how to put numbers on this now. The problem is that we don't understand what those numbers mean. We can quantify it, but those numbers still don't mean something to us. And the numbers are big, like I said. The US uses 101.6 exajoules of energy. Wow, what does that mean? It's a number that it's too big to put your head around it. Or we emit 33 gigatons of CO2, or 33 petagrams, or 33 times 10 to the 15th grams. That's not numbers. We can express it, we can quantify it, but we can't relate to it. So social scientists tell us that we need numbers between about 0 and 100. And if we can put them in that range, then we can start to better understand things, because 1,000's tough, but 0 to 100 we can work with. So if you're going to put it in numbers and you're going to start to understand how much energy you use, think about your daily life. Okay, so for example, how many liters, or actually it should be the other way around, how many kilometers per liter does your car get? I tried to go from miles per gallon in the US, but I got it backwards there. So how many kilowatt hours per day in electricity does your house use? Do you know the answer to that, or your apartment? If there's natural gas heating, how much energy is in that natural gas that you might use, or a propane tank or something like that? And so first you have to figure out how much energy do you use independent of industries and commercial buildings and everything else. How much energy do you use? And then Based on that, how does that translate to CO2? So you could look at, okay, how much food do I eat? How much energy my house uses. Our food energy might be kilocalories, house energy, kilowatt hours, cars. In the US, we use horsepower, maybe use watts or something like that. And we could translate all this to, say, a common unit of kilowatt hours. That's an energy unit. But do you know what a kilowatt hour is? Does that mean anything to you? And I would say, let's try and use food as a way to understand that number. So, you eat 2,000 kilocalories per day. In the US, we'd say capital C calories. In Europe, it's megajoules, 8.4 megajoules. If you use that energy to power 100-watt light bulbs, how many could you power? How many light bulbs can run continuously on 2,000 kilocalories per day? It's a test of not your ability to do the unit conversion, but just trying to understand how much food energy you consume. Most people guess somewhere between 3 to 5 up to about maybe 20 or something like that. And the answer is 1. And what that tells you is that you overestimate how much energy is in food and you underestimate how much energy you're using for something as simple as a light bulb. Now we can do that with carbon as well. We can take the energy in that food and combust it. That's what we're doing. We're extracting the energy out of the food and say how much carbon left our body as a result of eating that food. And the answer is about 2 pounds or about a little less than a kilogram of CO2. To eat, we're going to call this daily energy, 2,000 kilocalories, 1 daily energy unit. That's 1 food energy every day. And the carbon that comes out, 1C, 1 daily carbon emission. So everything you do now can be related to the food and the CO2 you emit. Okay, and now we'll just do a simple 0 to 100 game for these numbers of food energy and CO2. And keep in mind now, if I were to grow trees to capture just this CO2 I'm exhaling, with no energy use other than just exhaling, I need 15 trees just to take up the carbon you exhale. Now, CO2 goes other places, but in thinking about how we might use trees to capture carbon, it's an interesting number to keep in mind. So, carbon is a waste. CO2 is a waste. We started with water being a waste, then we went to solid waste, gather that up and try and contain that or burn it. Hazardous waste, gather it up, try and contain it or burn it. And our newest waste is CO2. And if you were to haul garbage out to the curb, you might haul out a couple of kilograms per day per person. If you were to use just a liter of petrol or a liter of gasoline per day, you'd be using about a little under a kilogram of gasoline, but you would be producing 2.5 kilograms of CO2. So just using 1 liter of gasoline every day for your car is going to produce as much waste as you take out to the curb or you throw away every day. And that's pretty amazing because where are we going to put that? We can put waste in a landfill, we can bury it, but there's no air fill up there to take all that CO2, and that's our problem. So this idea then is let's look at our water use, that's 1 gallon a day or about 4 liters a day, our CO2 emissions and our energy use, and start to look at how much we're using relative to those numbers, because we can never get below those numbers. So in the US, all the energy used in the US divided up per person is about 100 D. Okay, about 100 times our food energy. To put food on a table in the US is about 24 D. About 1/4 of all the energy we're using in the US is going to our food system. Well, that's good, but when you think about you only eat 1 D, but you need 24 times that, that's a big burden that really, I want to say, people don't think about enough. They think about commercial use, industrial use, just food use, which is includes all those things is taking up a lot of energy. A liter of gasoline is about 4D. So if all you do is use a liter of gasoline, that's already 4D of energy that you're consuming. How does this break down for the US? And I'll show you how it breaks down for Korea in a minute. You can see our 100, about 100D there, and 40 of that 100 is petroleum. About 30 is, or about a third of natural gas, about 10% coal, and then we have nuclear, biomass, and renewables. This is where all of it's going. And just our electricity grid is about, 14 exajoules, which in the US, exajoules actually gets translated to D units. They just happen to be the same. It's just a result of the number of people and so forth. So if we were to take that 100D and look at how much carbon came from those fossil fuels, we're looking at about almost 50 C. So it's about a 2-to-1 ratio, 100D, and you push out 50 C. Again, 50 C, rough numbers, a kilogram, that's 50 kilograms per person. If you wanted to lock that up using just trees, that's about 700 trees, or about 7 acres per person in the US, if we wanted to just pull that CO2 into trees, and we don't have enough trees to do that. So here you are, South Korea. Let's take a look. Here are your numbers in D and eventually C below. You've got 79D. US is at 100D. Of that nearly 80D, your C value is 48. And it's interesting because the C value in the US is about 48 as well. So actually, per person in the US and per person in Korea, we're releasing about the same amount of carbon per person. Now, we don't have the same population, but the per person lifestyle is what we're looking at. And the makeup of the energy you're using, again, is highly dependent on coal to a much greater extent than in the US. Where do we want to get to? There's a society called the 2,000 Watt Society, and if you convert that number into D units, that's about 20D. And they say we ought to be getting by on 15D of renewables and 5D of fossil fuels. So we have a long way to go, right? We're at 100 or 80. Denmark, I was just in Denmark, their D value is a little bit higher than Europe, but as I'll show you, their electricity grid is remarkably clean. So we look around the world in terms of not gigatons or metric tons or things like this, but rather our C values, and you can look and examine, for example, in China, their C value is about half of what it is in the US. But of course, the population there is so much higher that that makes them the largest emitter of carbon as a country on the planet. The EU, but what about a country like India? 5. Well, according to my calculation, my projection there, they're already there. They're where we want to be. And I'm sure if you ask anybody in India if that's a good number for the country, they'll say no. And this goes back to the point made earlier that, we have to think about the whole world in solving this, not just solving the industrialized nations. This is a really busy plot. It's trying to look at 4 areas in the world. It's the Middle East, ME, the USA, the EU, European Union, and China. The first bar is how much electricity energy is using, and the D above that is the normalized D for electricity. So you look at that first bar and you see in the Middle East it's about 6 per person, in the US it's 16, in Europe it's 7. So that is the electricity use per person in the US is about twice that of the EU. The electricity use per person in China is about the same as in Europe. What changes the situation here a little bit, though, is how much fossil fuels you're using and where those fossil fuels come from. And the difficulty here is that in China, the electricity grid is primarily driven by coal. And because of that, that drives up the emissions to be very high. Like I said, I was in Denmark. They have a 7 DE in Denmark, but their fossil fuel DE is only about 1. So 1 compared to 15 in the Middle East, or 26 in the US, or 7 in Europe, or 13 in China. It's an amazingly green electricity grid, and that's where we want to get. So the challenge here is to, again, on a personal level, is to look at how can we decrease our fossil fuel dependence for both electricity and for all energy. And so, looking at these numbers, about 80D and 48C, and trying to reduce that. And the way you reduce it, you say, is you go to electricity and you electrify. But unless you make your electricity grid green, you won't achieve that reduction in emissions. So let's make it a little bit more personal again. Let's get back to thinking about the car. Thinking about going to an electric car from a gasoline car, and what happens to to carbon emissions. So in the US, an average car gets about 25 miles per gallon. Well, let's not convert that for right now. Let's go to the D and C units. With the amount we drive every day, the average American is emitting about 21D and 14C just from driving a car with an average gas mileage. Now, if we all started driving a Toyota Prius in the US, we'd cut that in half because it gets about twice the gas mileage. If we go to an electric vehicle and we use the electric grid that's in the US, that drops from 7C to 5C. It actually uses more energy because those cars are heavy, but because of the electricity grid being cleaner than burning a gallon of gasoline, it's a lower C. How does that work on your grid here? If you are looking at an average vehicle in 4 kilometers per liter, or about 6C, and you switch over to the Tesla, then you could get down to about 3.3C. But it's actually more than just driving a gasoline car. That gasoline car is 2.9C, whereas the Tesla is 3.3C. Why is that? It's because your grid is sustained highly by coal. So if you look in this right-hand column, so the average car, this is again for the US, going from 14C to 7C for the Prius, and then using our electricity grid, it goes down to 5. But if I were to run that Prius, that Tesla, strictly on a coal power plant, that C would be 12. So you can see how your choice of vehicles, how your electricity grid impacts going to an EV. Because of this dependence, because of this dependence in this country, you don't get to actually have a net reduction in C by driving an electric car. So, I mean, I know many of you feel pretty good about electric cars, but that should double or triple your motivation for making the grid carbon neutral, or at least as close as possible, because the benefit, the true benefit of that doesn't come until you decarbonize your grid. So this is going back to Denmark. They don't drive very much, and they can get down to about 0.6C. So having a small country is helpful, I think, but also a highly green grid is very helpful as well. So let's think about where we can get from your, just from the things you're doing every day. You're going to eat. You're going to use, say, electricity to heat your apartment or home. You may use natural gas as an additional heat source. You have gasoline for your car, and maybe you travel, you take a trip a couple times a year to Jeju Island, or you go to the US, wherever you want to go on vacation. You know, if I do this for a typical person in the US, remember 100 D is the average for everything going on in the US. With just eating the food, heating my house with gas and electricity, taking a vacation, and using gas for my car, I'm at 57 D. 57 D just on the things I just living every day, it's 57 D. If I were to take my house and make it completely dependent on photovoltaic panels, and I cut out everything except that one vacation trip and eating food, the best I could do is 15 C. So that tells us that we need to think about our food system as a part of this, because we can use electricity from photovoltaics to power our car, to power our home and everything else, but we still have to transform the food infrastructure. And the reason for this high D unit for our food is that a lot of it's electricity, a lot of it's natural gas and petroleum, and so all those things get rolled up into the refrigeration of the food, the transportation of the food, the harvesting of the food, and so forth. Now I'm going to try and convince you that the food choices you make are important in this scenario as well. So in the US, you may not know it, but we eat a lot of hamburgers. Okay, you know that. If we were to eat a hamburger, an industrial beef hamburger every day, that would be 6C. 6C from eating a hamburger every day. But if I decided to eat this Impossible Burger, it's only about a half a C if I ate one of those every day. So even with our existing infrastructure, we could substantially reduce carbon emissions through that food choice, not because that food has less energy in it. The Impossible Burger and the industrial beef burger have the same kilocalories, but because of how it gets there and the process along doing that. Also, a lot of fish in your diet. We talk about fish being healthy and fish in your diet. How that fish gets produced is very important. So, for example, clams, mussels, oysters, and scallops, if farmed, have less than a half a C on daily food. But if you then catch them from the wild, it's about 2.5 C. So, when I started talking about these D and C units, you were thinking, I don't see it. But now maybe you're starting to see it, that liter of gasoline, that food choice, that vacation you take. Now you can start to see that your actions really do build into this infrastructure. And as consumers, you can influence companies' actions because you can choose lower carbon products. By the way, if you're thinking that a healthy diet will lower your carbon footprint, it actually doesn't, because of all the transport of all the vegetables and so forth. Actually, the best way to lower your carbon footprint is to eat an energy efficient diet. It saves about 3/4 of the energy, but it means you're eating a lot of carbohydrates and sweets and things that are not very healthy. So we have to find some sort of agreement between eating healthy and eating energy efficient. So, it comes down to a lot of, if we electrify, if we use wind and solar, we electrify, what happens in terms of the rest of the stuff? And a lot of this gets down to the petroleum, and a lot of that petroleum goes into transportation. If we were to continue to grow EV use around the world, and you can see here's different areas, China, Europe, North America, and the rest of the world, looking at the growth of the EV market in China is actually growing faster than anywhere else. But as I said, because China has a dependence on coal, that's not really going to help reduce gigatons of emissions fast enough. But let's just look at the US and where it's going. this would be a best possible case of exponential growth of EV vehicles in the U.S. and where they could get to in the next, say, 10 to 15 years. If we do that, we could get the number of EVs sold to be about 28 million by 2030, and you integrate under the curve and figure out, how much that translates to. Well, if we use electricity to power all those 28 million vehicles, that's about 0.34 exajoules of electricity, or about 2% of the electricity we produce. So it really, to electrify at the fastest rate, if we grow EVs exponentially, we're still only going to consume about 2% of the electricity made in the US. So I think our electricity grid could handle that. To put that number in perspective, Bitcoin uses about the same amount of electricity as the EV market would use. And that's more energy than more electricity than is used by, say, the whole country of the Netherlands. So please don't use cryptocurrency. Thank you very much. The other issue, of course, is energy storage. And this is somebody's house in State College, Pennsylvania. It's my house. And you see the green bars are what I produce from solar panels, and the black bars are what I use in energy. And over the year, my solar array on my house covers all my electricity use, but it doesn't do it every month. In the summer, I'm producing net excess. In the winter, I'm falling very short. And it's about 7D of extra energy storage I need to come up with in the winter. So how do we do that? Well, we use it through batteries, right, or large-scale energy storage. Let's again look at how fast can we grow energy storage. Can we grow it fast enough to help power that house in the winter? And if you look at where we are in the current battery numbers, we're way down there. If we project up, again, at an exponential rate, this is a semi-log plot. If we go exponential, we might get there to equal about, say, enough of the energy we're the electricity we're consuming, maybe 2.8 to 5 exajoules. So if we get there, that's maybe 2 out of the 7. So we can't get there fast enough on batteries, but that doesn't mean we can't try. And so batteries, then you think back to cars, right? Back to green electricity grids. These things are all linked together. So we can't just say, let's make our electricity grid. We have to also be thinking about how we store electrical energy or how we store energy. In the case of China, it's kind of worrisome because while, for example, in the US and many countries, the energy use has leveled off, China, as was mentioned, is not agreeing to limit energy consumption until about maybe 2030. If we go out by 2030, it's about double what it was in about 2010. So, there's tremendous needs to have good relationships with different countries, to not, blame anybody, but instead to work with countries to try and get agreements to lower those emissions and choose where you buy your products from to lower their carbon footprint. This is the energy grid in the US. It's about 35 exajoules, 35D. We produce 14D of electricity. Could we get to a nice green electricity grid like Denmark has by 2030? Well, we're doing some good things. In electricity, coal is coming down, but really natural gas is growing at the same rate to replace it. So all we're doing right now in the US, or for the past 10 years, is replacing our coal with natural gas. And the whole world can't do that. There's not enough natural gas to go around. But at least the coal use in the US is going to decline. Now, if we also then build in energy from solar and wind growth, we could increase the amount of electricity in the US by about 4 exajoules, so going from 14 to about 18 or 19. So we could grow that, but then if we did that, we're not actually reducing any of our natural gas because we're saying, well, we're going to grow and keep that going, but we do get rid of coal. So in this scenario, we can grow it and reduce carbon emissions through coal, or we can say, no, we want to cap those emissions, we want to reduce natural gas, and if we could do that, but I think it'll be difficult because of the demands on our electricity grid, we would get a change from 14 or 15 C for that electricity per person, right, to about 2 C. That's a pretty substantial reduction, and it's something that's very doable if we continue to grow at an exponential rate. I don't know what the growth rate is in South Korea, but I'm sure the Energy Institute here, with its emphasis on policy and technology, can help create the same rate of change here as well. Unfortunately, unless we also address the non-electricity sources, which are primarily petroleum and natural gas, we're not going to reduce our overall emissions enough, but we will make the grid at least greener. So, you know, this coming to the end here, thinking about solutions, this was a projection back in, I think, 2015 about how fast we could meet the 2-degree goal and what we would need to do that by, say, out to 2050, 2060. And you see that growth in nuclear, growth in renewable, those are been talked about. Energy efficiency, though, is as important or more important than renewable energy. And those are usually very inexpensive and very simple steps in many ways than the much more complex part of decarbonizing our electricity grid. But we don't get there, this is 2 degrees C, we don't get there unless we do something to address carbon capture and sequestration, that is, pull extra CO2 out of the atmosphere. How do we do that? Well, as mentioned previously, we have to move a lot of air through a lot of carbon capture units. You know, if we did that, if we used a gallon of gasoline or a liter of gasoline, let's use a gallon in the US. If we use a gallon of gasoline every day and we emit that CO2 into the atmosphere, then we use this to capture it and put it in the ground, the price of gas would go from about $4 or $5 a gallon, which is pretty good for here, $4 or $5 to about $14 or $15 a gallon. So imagine if companies had to pay for that carbon capture on a per gallon basis and charge the consumer. Well, you can't even raise the price of a gallon of gas by $1 in the US or in France or many other places without creating incredible social pushback. So direct air capture is probably not politically viable if it is scientifically viable. Yes, we can plant trees. 15 trees for 1 C, okay, that's a lot of trees, but the other part of trees are that they're not permanent. There are wildfires. There's nice forests that people then say, oh, if we cut that down, we can make some money, right? So it's not necessarily a permanent solution. One way to create more sustainable solutions that not only capture carbon, but also produce biofuels is to look at cellulosic fuels that have low nutrient requirements and very, very good carbon capture into the soil. So things like switchgrass. You can change a land use, say, from pasture land into one of these systems with miscanthus. You harvest the miscanthus each year to make your biofuel, which can be used for, say, airplanes, large transportation, shipping. And the soil that goes, the carbon that goes into the soil is helping sequestration. It's a double win. These issues that I've talked about in terms of food and the things you do every day, of course, don't take into account cement and steel use. We all know that this is a substantial part of our economies, and globally, they're still increasing. So we need some technology solutions here, hydrogen for steel making, alternatives to Portland cement for making concrete and so forth. We've moved from when we used to just use stone to concrete and steel structures. And so fundamentally, the way we make buildings today is much, much different than we used to. We talked about fossil fuel emissions, and the amount of carbon we emit each year is actually dependent on who you ask. If you ask the UN or you ask the International Energy Association, you get different numbers. But if you then add on other non-fossil fuels, other greenhouse gases, you start to raise those numbers up from, say, 33 to almost 50 or 60 gigatons equivalent. So while we're talking about fossil fuels largely, there's probably another equal amount out there in terms of land use disturbances and other emissions or lack of capture. And it's even a little bit trickier than that. We talked about methane earlier. You know, methane, people say, has a CO2 equivalent of about 25. But that's on a 100-year average. Actually, in about 10 or 20 years, the methane's gone. And so you can't really look at methane in a 100-year scenario. You have to look at its impact over, say, a 20-year scenario. And when you do that, the CO2 equivalent jumps from 25 to about 80 to 85. And so we would go from fossil fuel-focused emissions to other greenhouse gases and emissions to 60, and just redefining how you make that equivalency with methane would make it 80. So that's a real challenge. So, you know, I don't want to discourage you, but I do want to say that we need to keep this focus on all fronts. Finally, environmental and climate justice. The world is impacted by CO2 emissions and other greenhouse gases. While the average temperature may be increasing, we're going to see more and more of these heat islands, and people are going to need air conditioning, particularly in India, which is very hot and is already suffering from incredible heat waves, yet they lack air conditioning. And so if we put air conditioning in for everybody in India to address climate change, we just, of course, compound the problem. So we need solutions that work for everyone. We need solutions for flooding that works for everyone. We need to think about using trees as a way to cool neighborhoods as well, and we have to not use it as a sign of economic wealth, because in many cities in the US, or areas in the US, the wealthier neighborhoods have a lot more trees than the poorer ones. So it's also a sort of a climate injustice, because that means the poorer neighborhoods are going to be hotter. So let me finish there and just say this is something that obviously we know we have to work together, but you should feel empowered that your decisions can actually impact energy use. If everybody in Korea makes these conscious decisions, that's how you really draw down carbon without the need to have policy, without the need to have these laws. You can make those decisions. So we need to better educate ourselves about how much energy mass transportation saves us, or how much energy on carbon emissions electric vehicles save us. And let's make the best informed decisions so that we can also change policy and reduce those carbon emissions. And with that, I thank you for your attention, and if we have a few minutes, I'd be happy to answer any questions. Thank you.
Thank you so much for your impactful and well-organized talk. As usual, we have about 10 minutes, so we can entertain like 4 or 5 questions from the floor, if there is any. Okay, Professor Kim.
Jinso again. Thank you, Professor Logan. And I'm quite sure that almost all people here in the room knew about the Penn State, actually. Your presentation, your speech is very interesting and insightful. I think DNC approach, the presentation is very intuitive and persuasive. So it is very useful for both policymakers and citizens, as you said. Because, as you know, setting up a kind of easily interpretable or adaptable policy goal is important. I'm thinking about the decoupling between DNC and carbon leakage issue, because maybe your calculation, today's presentation, the C is maybe production-based carbon emission, which means it does not take the, for example, Chinese manufactured goods consumption in the United States or some other European countries. So if a country meets a carbon neutral goal, then that country, the people in that country may have no worries on the increase of D maybe, but there is still carbon leakage issue. Could you give me some comments on that point?
Yes. Well, thanks for that question, because it's a very, very important question. I often say when I become the dictator of the world, this is what I'm going to change. And if I had my way here, what I would change would be to put a carbon stamp on every product that you buy. So when you walk into the supermarket, you can look at this piece of fruit is 1C, this lettuce is 2C, this piece of meat is 5C. I would like that consumer information to be available so that you can choose what corporation or what item you choose, whether it's your shirt or a new pair of pants or something like that, that you look and you say, oh, this shirt should last, I don't know, 5 years. How long does a shirt last? And these numbers are not hard to come up with in terms of the energy to manufacture these. You know what's in the electricity grid, you know how far they're transported and so forth. And so I think the way to really make progress on the manufactured goods would be to find some way to label that. So like when I go into the grocery store, or when I go out for lunch in the US and I look at the menu and I look at that sandwich and it's 850 kilocalories, right? And then I look at the one next to it, it's 500. I choose the 500 one. Because I can afford to buy the calories, but I can't afford to eat them. And the same way we could do with our energy, with our infrastructure. So thank you. I think it's a really, really important topic.
Another question? Okay.
My name is Dong-won No. Yeah. I'm not sure that whether it is appropriate to ask you. Maybe I should have asked Robert here in the previous session. You explained that carbon capture and storage, you expressed sequestration is a very important technology tool, the carbon neutrality. But we know that there are some problems with the carbon capture and storage, especially the scientific and the technological uncertainty and the permanency. So, but you explained that the negative emission is should be very important for the carbon neutrality over the world. So, what kind of any alternative to solve the scientific and technological?
So, what are the alternatives to the existing carbon capture? Well, that's probably a whole nother lecture, I suppose. But it's I think you have to look to low-hanging fruit, because there are places in the world where you have point sources of CO2 where you could easily capture that, concentrated flue gases, not direct air capture, but concentrated flue gases. I don't think we've exhausted our imagination by finding different ways to capture that CO2. But for example, one way to not have to liquefy that CO2 and put it in the ground is to produce graphitic carbon when you're making electricity. And so you can just bury that graphitic carbon. Or you can capture it and reuse it so that you don't have to use other fossil fuels. So for example, turning that CO2 back into methane, using that methane in a combustion facility, recapturing it, going back to methane and so forth. So the combined sequestration and biofuels production, combined reuse scenarios can help do it, but it is going to be very, very difficult, and it's not something that we want to say, oh, we'll just do that and we won't worry about CO2 emissions. That would be a perilous journey.
Any more questions there? Okay, go ahead.
Okay, I am Jae Myung from KAIST, and thank you for your insightful talk today. You mentioned that about a quarter of U.S. citizens have some opposing views, and I think it's pretty similar in Korea too. There are such views, and among the students that I teach, there are students who are very pessimistic about the future. And one very tricky question that I get every semester is whether this climate change is reversible or not. And it's very difficult to answer because I'm not a climate scientist. And would this DNC calculations provide any qualitative reasoning on how I could better answer whether the whole issue would persist or not?
Yeah. Again, thanks for that question. It was addressed, I think, previously in the talk that maybe 1.5 degrees C is sort of a tipping point, and once you go past that, you do have very irreversible things. And let me just give one example of that, which would be the Arctic. Once you melt it, you don't reform it. And I think that's an example of where you have catastrophic irreversibility. And the same with areas that will continue to flood due to sea level rise. You will reach a point where you cannot build enough to keep the sea out. And so that will lead to mass migration, which will lead to other challenges as well. So there are both social and, I would say, physical challenges in our infrastructure that make things irreversible from the politics and policy side of things to just the sheer volume of water that we might have to keep out from flooding states, countries, areas of the world.
That's a quite alarming answer.
I wish I could have ended on a more upbeat note than that one, but.
Okay. Is there any further question that we have? Okay.
Well,
Okay, sorry, I'll make this quick. You mentioned that vegetarianism doesn't necessarily lead to a less carbon-rich society, but I remember watching this Netflix documentary, Cowspiracy, mentioning the direct opposite, making me thinking maybe this is just a great vegetarian conspiracy all again. What would you suggest the most appropriate diet for individuals to take for a more carbon-free and greener society?
Yeah, let me clarify my statement. I said a healthy diet. A healthy diet can include meat. It can include fish. A vegetarian diet, if done properly, can because of the huge carbon emissions from industrialized beef. So in that perspective, that's very important. But if you're eating wild-caught fish, and I gave you some examples there, that's part of a healthy diet, but eating farmed fish, for example, would lower the carbon footprint. Or eating sushi in the middle of Pennsylvania is probably not very carbon-free, but you could argue it's very healthy. So I think it's location and exactly what you're putting in your meal. But with the right meal, I agree that whoever said it, yes, you could definitely lower your carbon emissions. You could do that if you make good choices. We just need those labels on the items to make those good choices.
Okay, let's have the final question from Dr. Stoner. Dr. Sovacool.
I could be Dr.
Excuse me.
Stone. Yep. Professor Logan, very interesting, and I especially liked in your slide how you showed how grass-fed beef at the low end is still equal to the Impossible Burger. So I can still have my beef hamburger.
You can still have your hamburger and eat your carbon emissions too?
My question is a difficult one, and it's a lot of the presentation is about societies where we have consumer choice. But a lot of the world is in a liberal societies or authoritarian regimes. I'm thinking North Korea, Saudi Arabia, Russia, China. What do we do in those types of societies that have very different values and that may not give consumers information or choice?
Cross our fingers. That's part of, I guess I would say that, that's part of the, it's a whole world problem and we need to work together to do this. I think we do see signs in sort of top-down societies where things are dictated and eventually the citizens want change, that they start to create that change. COVID in China might be now the emerging example, where enough people are pushing back enough that eventually things will change. But the other side of that is if we can have enough information out there and access it, and we can find ways to access it, then people could still at least make choices. That's not a great answer, but you asked me a question that really isn't answerable. But thank you.
All right, with this, I would like to wrap up this, and then we all give him a big hands. There is an announcement for lunch. It's 12:05, and we will take our lunch till 1:30 p.m., which is about 90 minutes from now. And we will get together by 1:30 to get started with the talk from Dr. Sovacool. Enjoy your lunch, and then all invited speakers will go together with us to have the meal at different place. Thank you so much.
Ladies and gentlemen, we'd like to begin afternoon session. Please take seats. My name is Yang-kook. I'm professor at the School of International Studies at Hanyang University here. And at this session, we'd like to invite Professor Benjamin Sovacool. Let me introduce him first. To speak about himself, I think there are a couple of things I would like to highlight. First, he's now director of the Institute for Global Sustainability at Boston University. He's also professor at the Department of Earth and Environment at the same university. He's simultaneously having positions at a couple of other universities in Europe, in the UK, and in Denmark. And he's professor of Energy Policy and Director of the Sussex Energy Group, which is SPRU, at the University of Sussex. And also he's a Distinguished Professor of Business and Social Sciences and Director of the Center for Energy Technologies and in the Department of Business Development and Technology at Aarhus University in Denmark. To speak about his publication record, his surprising record of publications, I'm looking at his CV here. He has 529 referred articles, and he has 22 authored and co-authored edited books, and he has more than 100 keynote speeches in a number of places. He's not an engineering scientist. He's a, as far as I know him, he's a social scientist, but like I do, most of his work at the intersection of energy policy and technology. So he's looking at mostly, how energy transition, how energy issues impact social, economic, political changes. Please welcome Professor Benjamin Sovacool.
Thank you very much. And I have the toughest job to wake everyone else up after a delicious lunch, and I'll try to do my best. So, as Yang-kook was saying, I am a social scientist, so I'm going to give a kind of qualitative, interdisciplinary perspective on some of the many themes we've already talked about today relating to net zero policy. So I'm going to talk to you about 3 core insights from a project we have. I'm going to talk about co-impacts or co-benefits, policy, and then finally, and look at those slides, gentlemen, justice, or as I like to say, justice, in this particular slide. And I wanted to start here by just telling you that most of the time, many professors give talks. We give data from other places like the International Energy Agency, or we talk about papers and projects that have happened in the past. This is really exciting for me because I'm here talking about a project that's currently open and ongoing, and it will be ongoing for the next 4 years. We have a European Research Council grant called GENI, which will run for 6 years. Lots of discussion today has been about what I really think are the true, meaningful solutions to climate change, which fall into the category of mitigation and adaptation. Mitigation is stuff like renewable energy and electric vehicles and energy efficiency, and adaptation is things like building resilience to climate change with seawalls or flood protection or better, diversifying crop patterns. Those are kind of plans A and plan C. GENI is really interesting because it says, what about plans C and D? What if mitigation, adaptation don't work? What can we do? What does humanity have left? And so it's a 6-year project that looks at all of the technical, social, political, legal, and ethical dimensions for these very radical technologies. And I'm amazed we got funded because, as you can see here, we have 4 PIs. They're all men. They're all white. So we have definitely a gender problem. But as I like to joke, we at least have diversity of hair color. And so we have Greg has red hair, and Yan has brown, K1 has gray, I have none, as I like to say. But more importantly, we have a real diversity of disciplines. And so in the GENI project, I'm there on the left doing stuff like qualitative social scientist. K1 is doing integrated assessment modeling and engineering. Yan is doing quantitative social science, so evidence synthesis, machine learning, topic modeling. And then Greg is doing more political science, as well as kind of econometrics of innovation. Why are we concerned about this? We've kind of, all 3 keynotes have kind of showed you the same slide, but in different ways. And this is a kind of stylized graph. It's not a real graph, but it's kind of showing you at a meta level what we have to do by the end of the century. And you can see, right, the argument is not only do we need to cut emissions dramatically to get to zero, what do we do post-2050 when we actually have to go net negative? So we have to start to remove CO2 out of the atmosphere, or we still have things that will rely on carbon, like industrial processes, aviation, freight, other hard-to-abate sectors. So we'll have to find ways to store that carbon, should we want to continue to have that type of activity. And that does mean that in most of the integrated assessment pathways, we don't just do net zero, we do negative emissions, carbon removal, greenhouse gas removal. And probably post the end of the century, we'll have to do it a lot more and more and more to help restabilize the climate and potentially even start to reverse the impacts of climate change. So it sounds pretty cool, right? And that's largely why you have now this of work that uses geoengineering or carbon removal technologies, which are fundamentally different than mitigation and adaptation. And they're extremely controversial because many people argue if we can somehow do these things, maybe we don't even need those things at the top. And also, some of these things could actually be very cheap. So, International Energy Agency told us 2 years ago the cost of net zero energy systems is $100 trillion by 2050. So the cost of climate mitigation, $100 trillion. Adaptation needs, we already heard, could also be in the order of $1 trillion a year. A widespread stratospheric aerosol injection program could cost $10 billion. $10 billion. And you could also have fairly large things like negative emission systems that also could only cost $500 billion. And so you start to see these arguments are the scalability and deployability are much quicker, faster, cheaper than other options that we keep obsessing over, like mitigation and adaptation. And this helps show you a typology of how many of these options sit. Some are very natural, like biochar, forest management, soil carbon sequestration, maybe storing marine carbon and things like blue carbon, kelp, and seagrass. Others are very kind of engineering heavy, like direct air capture and CCS, and this is BECCS, bioenergy with carbon capture and storage. And still others are kind of very much connected to the minerals and extractive industries like enhanced weathering, enhanced mineralization, or ocean alkalinization, where you try to reverse ocean acidification. And another way of reading it is on a kind of scale of less costly, more socially acceptable to more costly and maybe less socially acceptable, but also inversely, these ones have permanence issues, right? As other speakers have said, wildfires, pests, bad forest management practices, whereas these ones on the right are more permanent. So again, you start to see this kind of nest of different criteria are pushing us to do different things as we try to actually help fight climate change. And one of the options that we're actually studying doesn't sit here because it's literally out of this world. There's even people proposing space-based solar geoengineering, right? Largely because it can work with ongoing initiatives like Alpha Centauri sailing missions and colonizing Mars and Artemis. And you can see we actually did study one option with a recently published article called the Interplanetary Sun Shield, which would sit at the Lagrange point between the Earth and the Sun. And this sun shield would help dim the sun to then lower temperature, which means we could actually undo 1 to 3 degrees of temperature change. And in the review we did of this study, we found a whole host of earlier studies going back 30 years that have talked about this type of an approach in outer space, whether it's using Dyson dots or spacecraft or sun shields or other whole different types of really weird technologies. And this shows you a very recent proposal by Airbus, Space and Defense, and the Institute of Space Systems for the Interplanetary Sun Shield. And you can see all of the other exciting things on that graph that it would enable: moon-based economies, robots in space, solar sails, as well as the kind of launch of a space or moon-based economy, asteroid mining. In the study, we did expert interviews with people from NASA, Raytheon, Boeing, OHB, which makes integrated spacecraft in Germany. And these are just some of the quotes from the advocates. Look at this one. It's a Plan B climate airbag solution. It's not meant to stay there more than a few years, but at least it's a way to reduce near-term emissions. You can see up here, up on the right, it doesn't involve putting chemicals into the environment, and it can be tweaked, and it would cost less than $1 trillion. So we could ostensibly solve the climate crisis with the sun shield for a very, very, very low cost. So in the Genie project, as a whole, we do consider 20 different technologies, which makes it a very multi-technology study. We consider the 10 different types of carbon removal on the left and the 10 types of solar geoengineering on the right, including space-based reflectors and high-altitude sunshades, as well as things like ice protection, as well as things like cloud thinning, cloud brightening, and aerosol injection. And what have we found so far? So we've only been going for a year and a half. One of our first studies interviewed 125 knowledgeable experts, including experts from, I think, both Penn State and MIT, made it into our list. So only the best experts in the world. And we took a socio-technical approach that says that, well, geoengineering and carbon removal isn't just about the technology. It's also about political issues like competitiveness, the ability to weaponize the technology, security, regional cooperation and governance. It's about social and environmental things, like how does it integrate with renewable energy, how much will it cost, how permanent are emissions reductions, as well as financial and economic issues of things like business models and patents and intellectual property. And doing that, from our interviews, we found there are actually 107 distinct co-benefits or co-impacts to doing this type of carbon removal or solar geoengineering. Now, we use the word co-impacts because it's replaced the word co-benefit because there can be a negative. So a co-impact is an unintended positive or negative side effect, very close to an externality or a positive or negative spillover. And again, we're using qualitative data here as well. So our qualitative data is based on the expert interviews. So again, it's, there are certain assumptions that go into it. But from that expert pool, you can see, it's actually better here. This shows you the positive co-impacts for carbon removal. Yes, and this is the negative ones from geoengineering. So you can see one of them has more positive, which is carbon removal, and one has more negative. But what I like more is out of the 120 or 117, we explored 20 in depth. So what you see here on this right graph are the ones that came up the most. So this came up with the consensus of the interview data, because when you do qualitative work like this, you do the interviews, you transcribe the interviews, you code the interviews, and then you thematically analyze the interviews. And you can do frequency counts. And so you can see all of the different ways on the top that these options can deliver positive things beyond climate protection, like providing decent work and jobs in sectors like the extractive industries or marine economies, or enhanced protection of life above land, because you're maybe cultivating better types of integrated forest management, or things like ecosystem regeneration and soil management are good for all species. Those things have huge co-benefits at helping rainforests and helping other ecosystem services. For things like solar geoengineering, you're also boosting aerospace industries, satellite industries, and aircraft industries, because you're having to deliver things like high-altitude dispersal of particles. You could also unintentionally do things like enhance crop production. Biochar here has potentially positive impacts on how you can grow certain crops. Same with enhanced weathering, which can increase yields in early trials in places like Australia by about 1 or 2%, if you're talking things like sugarcane or soybeans. You also have a whole variety of negative co-impacts as well, like energy penalties, right? When you have CCS on a power plant, there's sometimes a 10 to 30% energy penalty because you have to run the equipment. So I think this shows, I think at a glance, firstly, how these technologies have co-impacts that well extend beyond the technical domain. It also shows you a really weird mix of positive and negative, which helps explain why they're so contested. Because the advocates are only going to focus on the intentional positive ones, and the opponents are only going to focus on the unintentional negative ones. And each of them is obscuring other elements in ways in which the technologies could interact. It lastly explains why we've seen so much social opposition to carbon removal and geoengineering so far, because people do see some of those negative co-impacts. And this is an assessment that we did of more than 40 early stage experiments all across different types of geoengineering, whether it's ocean fertilization or cloud brightening or aerosol injection, ice protection, enhanced weathering. With a very recent one there, this one up here, Scopex, was just suspended last year. This is Harvard, by the way. Harvard University's trial of stratospheric aerosol injection was canceled because of opposition from the Sami community in Sweden. And so there were real concerns, and it was just launching one balloon full of a few kilograms of particles, and they had to cancel the experiment. So social opposition can be very, very, very intense at a lot of these. And what we found in our study are a variety of themes. By the way, OF is ocean fertilization, MCB is marine cloud brightening, SAI is stratospheric aerosol injection, EW is enhanced weathering. And we kind of found, these kind of key strategies that both opponents and proponents use. Opponents of the projects are often drawing on things like unintended consequences, the risk of accidents, earthquakes, or uncontrollable, irreversible changes in the environment. And what's fascinating is that the proponent's solution is to just camouflage the project and not call it geoengineering. You'll call it salmon restoration. You'll call it enhanced adaptation. So you'll just kind of use different words, and in those projects that they don't use those terms, there's no social opposition. So it's already starting to kind of point towards rhetorical strategies and playbooks that you could use on both sides of the debate. You also see the expansion of the actor space as citizens, indigenous groups, lawyers, litigators, students are all getting involved, which helps open up the discussion but also make it more polemic. So that's the first finding. While we think these technologies are about technology, they're actually about social controversy and a whole array of political, economic, and environmental co-impacts. Second one is really fun, and this is a survey we did also last year, just published in October, where it was some of the experts we interviewed also took the time to fill out a survey. Not all of them. So you can see here we have only 74 experts, but still, from more than 60 organizations with, look at that, 810 years, of experience working in the area, as well as, there is a bias here towards universities, but at least some private sector, NGO, and civil society involvement. We at least had some of it. And one of the questions we asked straight off the bat of these experts, by the way, these experts had to have published either high-quality peer-reviewed articles on the topic or patents. So these are kind of top, these are called elite interviews. People whose life it is or career it is to know about these technologies. So they're extremely knowledgeable. First question we asked, do you support carbon removal? Look at that. By the way, this is negative emissions technologies. 90+% said, we will not stabilize the climate without these technologies. That's a consensus. Look at the other way for geoengineering. SRM is solar radiation management. 60+% said, no, we do not need these technologies. So there's already a split in the experts. They like carbon removal, and they don't really like solar geoengineering. Then we said, okay, when you talk about carbon removal, which ones are desirable and optimal, which ones are not? And this is just showing, I think, the median scores. So you could, of course, present data in different ways. But you can see afforestation, soil carbon sequestration, and what is that, ecosystem regeneration are all extremely positive. You have a middle set of things like direct air capture and biochar and CCS, which are kind of okay. And then you have these two, marine-based carbon approaches, because people like the oceans to stay pristine, and ocean fertilization or alkalinization that are very disfavored. So already you can start to get a rank order of what the experts say they think that they like and they don't like as we put together a portfolio. And you see this similar rank with solar geoengineering, where they like a lot of albedo modification and maybe things like ice protection and cloud brightening over confined marine areas. Middle ones like aerosol injection or albedo management in deserts. And then what they don't like are the space-based ones and the sunshades. And I'm guessing, I wouldn't dare put words in Robert and Bruce's mouth, but I'm guessing that they'd probably rank order pretty similarly if they were asked as well. Then we said, well, how much is it going to cost? Because it's not just about what the experts say they like. How much do they think these options will cost? And I think here we said 2050. And I'm showing you the min and the max. And so you can see that things like soil carbon sequestration are able to operate very cheaply. They can displace a ton of carbon for lower than $50 per ton, whereas others, look at this, CCS will need between $50 and $200 per ton in order to be cost effective and work by 2050. And direct air capture, which is like the poster child right now of discussions, would need 100 to 500 per ton. So you're already getting a very different sense that some of these options could just be too darn expensive, given that the price of carbon right now is about $15 to $25 per ton, depending on the market and whether you count it as an offset, whether it's in euros or dollars, and whether it's fungible or not. The other way, so with negative emissions, you calculate cost and optimality per gigatons. But for space-based or solar geoengineering, it's temperature reduction. So again, here, sort of similar thing where we tried to look at, how effective are these at reducing temperature? How much degrees of change of temperature could they save? So the higher the bar, the better it is. The higher the bar, the more the technology can actually effectively control temperature. And so obviously things like aerosol injection, and I think this is ice protection, are deemed as pretty good. And then this is albedo management is in the middle, and then the rest are pretty poor, with some, like sunshades, again, doing very, very poor. And then finally, I really like this question. We then asked this prominent pool of experts, when will the technology be ready for commercialization? And we even gave them a definition, 20% of market share. So when do you think each of these technologies will surpass 20% of the market for climate protection? And again, these are box and whisker plots, so they show you the min, the mean, et cetera. So, and they're giving you outer ranges. So really, the sweet spot is kind of here in the middle. But the upper range is also very, very interesting where some of those dots are. And again, I want to focus just here on direct air capture, because this has captured a lot of attention here. Our evidence suggests that it's going to be at least between 2040 and 2060, and the 75th percentile is 2090, and some people even say 2100 at the upper end of the extreme estimate. So again, it starts to see just how few are actually available in the near term, and just this is 2030, so this is still about a decade away when we actually collected the data for the study, and only like 2 options actually are ready. It's ecosystem restoration and afforestation. So it also starts to unpack how realistic some of these options are or aren't. And for some of the options, a lot of our experts still said never. Because the data earlier is presenting you averages, means and medians, but that belies the fact that in some cases, there was a huge proportion of people who just put 0. Right? We don't think it will ever reach commercialization, especially sunshades, the sun shield, ocean fertilization, and things like albedo modification in clouds. The final 2 things we did with our wonderful experts, we put them to work, is we also asked them to talk about risks and barriers. So risks would be negative things that each of the technologies does, and we asked them to just do composite risk scoring. So we didn't break risk into political risk or technical risk. We just said, what do you think the ultimate composite risk is for each of these technologies? And again, you can see further out on the spider diagram is greater risk. So the riskiest, sorry, David Keith, is aerosol injection, according to our experts. Second riskiest is high altitude sunshades, as well as space-based reflectors. They're pretty high up here. And then you have a whole host of ones that are moderate risk, and then the least risk would be here, which is, things like, should be the natural ones, like, there it is. Afforestation is a 2, right? And where are you? Ice protection is a 4. So they're only of moderate risk. And we finally said, this was the last question, what are the barriers? And we've given you a traffic light system here to help interpret the data, because they could rank barriers on a scale of 0 to 5. And while we had a composite risk question, which was overall risk, we then wanted this question to be more specific so you could get into some of the specific dynamics of what may be a barrier, whether it's difficulty in scaling, or difficulty in storage, or social acceptance, or regulation, or system integration, or financing, or having an adequate market, right, or environmental risks, or then other. And what you can see here is obviously these options pretty much have the fewest barriers. All of your natural options at the top, forestation, soils and biochar, blue carbon, ecosystem restoration, fare pretty well. They don't have a lot of actually significant barriers. Whereas you can see other options here have a lot of red. And so the 2 or 3 that are deemed having the most significant barriers, ocean alkalinization and fertilization, direct air capture, and CCS. Now this is very problematic because in each of the earlier 2 presentations, there was sort of an implicit assumption that we'll have some sort of carbon storage by 2030 or 2050. And this is telling us that, well, there's still going to be some pretty significant barriers there as well. And finally, I think it's really interesting as well that not all of the barriers are technical. A lot of them are non-technical, especially with dealing like things like social acceptance, social license to operate, and community well-being. So what are our ultimate findings before I talk about justice? So I think first of all, it's weird. Other people who do expert elicitation processes like this on like small modular reactors or solar photovoltaics, it tends to be very positive. Experts overestimate. They have optimism bias. Here, it's almost the other way. Unlike those types of things, our experts are pretty harsh. They're kind of like, they're all rubbish. And very, very few they think will actually reach commercialization at cost or at scale or in time or without significant risk or barriers. You can still create a portfolio of hierarchization with the different criteria from the expert survey, and that does suggest that these 3, forestation, ecosystems, and soils, have a really, really optimal list of benefits. And then it's albedo modification with grasslands, human settlements, and cloud brightening are more desirable than other geoengineering options. And then, you know, it also aligns with which ones have the greatest potential. So this one says that what do they prefer, but this one is more like what's the ultimate potential of these options to sink carbon or actually minimize temperature change. And again, it changes the order a little bit when you talk about potential. It could be afforestation, ocean fertilization, and BECCS, right? And, you know, these numbers are quite large. There's good evidence you can't really add them up together because they'll, you know, land is fungible and some could have mutually exclusive trade-offs. But, you know, as the climate scientists will know, 165 gigatons of CO2 is a massive number. I think we're globally emitting about 55 gigatons of carbon dioxide equivalent, right? So these options have the potential to arrest 3 or 4 years worth of global CO2 emissions. And if you still had to do geoengineering, our experts are telling us that aerosol injection, albedo management, and space have the best potential, and they could even offset a 2.5 degree temperature change, which is actually very significant. It's also interesting when you start to talk about those cost numbers, but in comparative efficacy, because policymakers don't just want to do cost-benefit analysis, they want to do cost-effectiveness analysis. Is what I'm spending money on the most effective use of my resources? And look at this. When you start to do these types of comparisons per ton of carbon displaced, soil carbon management is 60 times cheaper than BECCS. And yet we still only talk about BECCS. Or look at this one. Ecosystem restoration is 18 times better than CCS. Yet very few people are talking about an ecosystem restoration industry or a wave of ecosystem restoration. They're still obsessing over CCS and CCS. And blue carbon could be 35 times more cost effective than DAX, but we're still obsessing over DAX, right? So again, you're starting to kind of see what's hot and what people are talking about publicly doesn't necessarily align with the options that may be more mundane, that have much more potential. When you talk about timing, this is also very worrying. If you buy the argument we're in a climate emergency, and some of you have heard about the Anthropocene, which is arguably the current era of humanity, you may not have heard that some are even calling it the Necrocene, the area of mass die-offs, because we have species extinction and climate instability. That means we probably have a carbon budget of 5 to 7 years. And that means that, you know, as both the earlier speakers said, if we're going to reach 1.5 degrees, we have to start now at rapidly cutting emissions. If that's true, only afforestation and soil carbon sequestration are available by 2035. So only 2 of these options are near-term options to fight climate change. All of the other ones are potentially off the table if you want to lock in net zero within a decade and a half, which is a very sobering finding because it implies we take most of these options off of the discussion for financing, policy development, and diffusion. And in very simple terms, if you buy our data, many of the most discussed options like CCS, direct air capture, and BECCS, and almost all of the solar geoengineering options are post-2040 or 2050. So they won't be ready in time, is the argument. And some, like my beloved Sunshield, is like hitting 2070, when I probably won't even be alive anymore. Which means they're not available for use now. And some of them may never reach commercialization as well. All right, last bit before we turn to a hopefully fruitful and dynamic question and answer session is justice and equity, which is another really interesting theme from our research. And here we're going to our full sample of expert interviews, and like I said earlier, 20 different technologies, and the same sample as I presented in terms of the first study on co-impacts. This actually shows you all of our questions from the interviews. Obviously, I'm going to be only talking about justice right now, but if you're interested in some of these others, we have papers on actors at Nature Communications, Earth and Environment, and risks in risk analysis, and coupling, and technological forecasting and social change, and in innovation at Research Policy. So there are other elements of our data that are very interesting. But for this particular paper, question 6, we're dealing with all the data from our experts where we asked these 2 questions. What equity and justice concerns arise with deployment? What vulnerable groups are affected? And then from this question, what risks do these options entail? Some of the issues were equity-based or justice-based, so we're kind of able to tap into that question as well. And to do so, in the paper in political geography, we set up what the literature says so far. And the literature, it is growing. There are dozens of studies that do talk about justice, negative emissions, geoengineering, but kind of in a limited way. You got a lot of people talking about procedural justice, so issues of planning, free prior informed consent, representativeness, elite biases, expert top-down driven policies. You have a discussion about mitigation deterrence. You gotta love that term. It's the moral hazard that if we think we have plan C and plan D in our back pocket, we won't take seriously climate mitigation. So it will deter the fundamental drivers of climate mitigation. And then in 30 years, if we weren't able to deploy negative emissions, we're done. We've missed the ability to fight climate change, and we're stuck in a world with 3-meter sea level rise and wildfires and droughts. And some studies talk about distributional justice issues, just that there's unfair distribution of costs and benefits between the private sector and the public sector, or between, say, rural agrarian communities and urban communities, or between those who have the technology and those don't have the technology, and a little bit of discussion about NIMBY, which is not in my backyard sort of sentiment. So this is a good starting point, but we thought it was incomplete. And we thought conceptually, you're still missing lots of dimensions of justice, like recognitional justice and corrective justice and cosmopolitan justice and capabilities. And so we instead created 2 different types of frames to reinterpret what justice means. The first one is called whole systems justice. So this takes all of these technologies, direct air capture, enhanced weathering, and it doesn't just look at where they're used, it looks at their entire supply chain. What are the minerals, chemicals, and other types of inputs, perhaps it's mining, gravel, that they would need, who makes them, who works in the factories, and who owns them. How are you transporting a lot of the materials? For instance, bioenergy with carbon capture and storage needs huge transport corridors or pipelines. For bioenergy, direct air capture is going to need hundreds of millions of kilometers of say, carbon pipelines. Maybe they're coupled to hydrogen systems as well, or offshore wind. You also have issues behind the scenes of planning and policymaking and governance, and then you also have issues of waste, especially things like electronic waste or things like hazardous waste. And we found from our expert data that you have pretty immense justice risks at all of these different domains of the life cycle stages of our geoengineering options. And the literature talks about how these create sacrifice zones, right? Communities that are kind of at the front line that suffer debilitating impacts, as well as what's called peripheralization, where you push noxious externalities or social effects to the communities who are least able to oppose them because they're politically marginalized, economically marginalized, socially marginalized, or culturally marginalized. And you can start to get a sense for some of, for instance, the inequities that could occur if we do reach a net zero geoengineered world. For instance, according to our qualitative data, if you were to use enhanced weathering, you would have an impact globally equal to global strip mining for coal, right? So it's already starting to see, you could actually double the size of the mining and extractive industries. Or you could see a 50 to 80% increase in fertilizers, which we don't want, because a lot of those use fossil fuels. In terms of ownership, there's a concern that it's just billionaires or highly integrated technology companies that will do it for profit, just like pharmaceuticals, that won't then let it diffuse to the global south. Or that some of these options could result in extreme poverty or unemployment. For instance, large-scale forest plantations, where you manage trees, could displace hundreds of millions of smallholder farmers who try to farm from the forest. Is the forest for farming or carbon storage, right? Either one will shape different forest trajectories. I'll talk more about transport in a second. Policy and planning also has a whole bunch of issues about accountability, liability, future generations. Operation and use has issues of accidents, but also termination shocks, that if you stop doing the technology, the climate could rebound faster than it would have changed naturally, which is even worse. It's like rapid, aggressive reclimate change. And then you have things like earthquakes and accidents, CO2 can leak and bubble up, as well as things like hazardous waste streams. I just want to focus on one of these to give you a sense for the richness of our data. So this is only transportation and construction. And I put this here because it's probably the most bland. You're like, how can transportation and construction have justice issues? Well, here are some of our quotes. For negative emissions to reach the scale we need very super continental scale managed plantations that are harvested on a short rotation cycle, and this could need catchment areas of thousands of square kilometers. They went on to say, how big? The size of India. So just transportation and construction networks could be the size of almost an entire subcontinent. What about indigenous groups, where about 80% of different extractive industries are located? There won't be any trust for deployment of these options in tribal lands. People will doubt that it will help them. They could even be seen as colonialism to displace local people from their assets. And by the way, the R is just the respondent number. Our interview respondents were anonymized to protect their identity, because as you can say, they're saying some pretty seriously critical things about the technologies in question. And this one as well, which is that if you were actually to roll out CCS, you'd be able to maintain the current distribution of fossil plants. So it's only rewarding incumbents, and it's only protecting fossil fuel assets. The communities that have been built around coal and gas would prosper, but it would also imply continued or even additional use of fossil fuels. So basically, fossil fuel communities become addicted to fossil fuels and stay fossil fueled forever. And this then just shows you at a higher level, synthesizing across the data for both carbon dioxide removal, as well as things like carbon dioxide removal that are more engineered, all of the different ways in which it fits our data from the framework. Now, the last thing I want to say is also not necessarily about whole systems impacts, but about different types of justice. So the other thing that we did in the study, this is what happens when you try to publish in a geography journal, is they keep pushing, the peer reviews keep wanting more conceptual novelty and conceptual novelty. We also tied together from the literatures on geography, energy geography, political ecology, and sociology, perspectives from the bottom up and the top down. So top-down kind of approaches that are expert-driven often identify these justice concerns: colonialism, exclusionary policymaking, structural patterns of dispossession, unfair trading patterns, and work on the micropolitics of communities often deals with a whole other set of concerns like community structure, land grabbing, migration, class contention, power flowing away from rural communities to urban communities. And so what we tried to do is capture it all. So we tried to use a framework that captured injustices from above and below, but also using more than just distribution and procedure to also include recognition, capabilities, and responsibility. So this is, conceptually a more diverse array of justice issues. And you can see again here is how they all fit according to these different justice tensions. And you can see again a whole host of burdens which basically imply it's a justice nightmare. Like if we think that these new technologies will somehow be more equitable and more just than the current technologies we have, we're in for a bit of a wicked surprise and are opening ourselves up to a whole variety, concentration of profits and dependence, the risk of perpetual accidents and leakage, lack of adequate compensation for communities, unfair, non-representative planning and policymaking, and so on and so forth. So what do we conclude? There are three other ways that we're now pushing the research to go as we think about a net zero world. The first one is that even in our studies, people tend to talk about technologies one at a time. The risk of CCS will be this. The risk of direct air capture will be this. The risk of enhanced weathering will be this. When in reality, when someone starts to do cloud brightening, this is cloud brightening near the Great Barrier Reef in Townsville, Australia, that's just one of a whole portfolio of options or a cocktail of options. And how negative emissions intersects with solar geoengineering is very, very misunderstood, poorly known, as well as how different negative emissions will interact with each other and how geoengineering will interact with each other. So it creates a complex, multi-pathway, intersectional array of options that are impossible to model. I don't think any integrated assessment modeling community handles even more than 3 or 4 of these, let alone all of them. So that's the problem. Real deployment is going to be thousands of actors doing this, but it is outside our capabilities of modeling and prediction and data collection. What does that mean? It's like that old joke about the economist searching for their car keys under the streetlight because it's the only place they can see. These are all the things that we can't currently see, but they could be where those keys are hidden. The second thing is this new term that's come out of the literature, and I really like the National Academies picked up on it last year in a report on geoengineering. It's called risk trade-offs. Not risk trade-offs, risk trade-offs. What's that other risk doing after the hyphen? That implies each of these options has a risk it's trying to eliminate, but it eliminates it only with another risk. So you're never eliminating risk, you're redistributing it or shifting it to another community, to another future generation, in time or space. And you can see at a high level, here are all of the potential benefits. Here are the risks that these technologies can solve, right? Huge emissions reductions, huge potentially local improvements to the environment, a huge expansion of innovation and jobs and competitiveness. But in doing so, they unleash a whole set of other risks as well. Weak governance, weaponization. We found that some of them could even be used to do weather control. Or some could even be used, like marine-based carbon removal could kill fisheries. So you could actually have, nefarious actors deploy them intentionally to actually damage the protein supply of a whole country. We even had people talk about how you could have hackers try to go in and affect the software controlling carbon reservoirs and saying, pay me 10 million bitcoins or I'm going to release 20 gigatons of carbon, right? So you haven't eliminated anything, terrorism, hacking, weaponization, insecurity. You've only shifted it to a different type. And at a very meta level, a lot of the land-based carbon removal options aren't eliminating the risk of climate change. They're transferring it to the land, right? Rather than control emissions, now we have to control forests and land use practices and agriculture and wildfires and pests and better management. So again, risk abounds. It is never eliminated. And how we better conceptualize those risk trade-offs, let alone minimize them, is another very important research horizon. And finally, and the last one, is what we're currently doing right now is in literally this month and next month is in Work Package 3. This is the entire secret blueprint for the Genie project. And I'm leading Work Package 3 about social acceptance. And we're running a large-scale survey in 30 countries with 35,000 respondents. So, and those countries include a mix of global north and global south. We have all of the BRICS except for Russia. Brazil, China, India, South Africa. Dominican Republic, Israel, Singapore, Egypt, Saudi Arabia, but also 10 European states, Germany, France, Norway, Sweden, and so forth, the United States and Canada. And then we're coupling that as well with 44 focus groups in urban and rural areas across most of those countries. Oh, Kenya, Nigeria are also included. And so it's going to be probably the first real global assessment that doesn't use weird countries, as we were talking about earlier, that really attempts to look carefully at how social knowledge, familiarity, opposition, acceptance, values, risks, and policies and governance are perceived by a representative sample in 1/5 of the countries in the world. And what we're also now doing in the project, predominantly through my colleagues at the International Institute for Applied Systems Analysis, is creating a knowledge hub where we're trying to share data, as well as do things like our scenario explore, very similar to what we've seen earlier. I think MIT has something similar with their pathways. EASA has a really good one that also lets you see different pathways and projections for a low-carbon world and what they might mean. And we're really working on visualization and making it understandable, because this stuff is complicated to a normal audience. So those are the 3 exciting areas that we'll be doing work on going forward, looking at portfolios and cocktails, looking at risk trade-offs, and looking at social acceptance from normal people all around the world. And with that, I am right on time. Thank you.
Okay, thank you very much. We'd like to spend about a little more than 5 minutes. I'd like to take maybe a couple of questions. If you would like to ask questions, please identify yourself and ask questions. Yes.
Both of you.
Very informative. Thank you very much. One of the solutions you mentioned was the blue carbon and seagrass. And oceans are heavily influenced by the presence or absence of nutrients. So, in other words, things in the ocean fight for nutrients, and there's usually one limiting nutrient, they say. There can be more, the iron fertilization approach. But in the seagrass approach, could you elaborate on how that works a little bit more? Because I'm not as familiar with that one.
So I don't know much about it, because I'm not an expert in marine-based carbon removal, but my sense is there's kind of 2 types. The first type is just kind of managing and restoring areas that have been degraded. So they're it's like natural ecosystem regeneration, but it just includes sea forests, kelp, and things like that. The others are plantations. The others are more just like fish farms. You would create new parts of the ocean that just grow and sequester carbon through seagrass. And so there could be a whole industry of getting carbon credits and other things where you deploy them all throughout, say, Indonesia, right? Other littoral coastal states that have a lot of space and could also use, about Bangladesh comes up as well, Myanmar and those types of places.
The other one I've heard of is sort of deep ocean growing of kelp or seagrasses and then letting it sink down into. But the other part of that is you lose all your nutrients sort of permanently as well. I mean, the carbon goes away, but the nutrients go away as well. And so, do we really want to deplete our oceans of nutrients in that sort of way? I mean, it'd be fine if it was in the Gulf of Mexico because we got too much down there, but a lot of other places you don't. So, I mean, I could see why the ocean community would be a little reluctant at trying to really massively manipulate a system which has already been massively impacted.
I completely agree. And there's also a lot of, when we do the social acceptance work, we've gotten some of the survey results now, and ocean-based protection has some of the least support, because you don't mess with people's beaches and oceans. That said, unlike most of the other things we've got in our arsenals, there are 2 carbon removal options that could help save the oceans. Those are enhanced weathering, ocean alkalinization. Both of them help reverse ocean acidification. So there it is, kind of in the long term, that could also be very healthy for the ocean. So it is this weird risk trade-off. Do you rob nutrients, but at the same time stop acidification? So you're solving one threat, but not another. But at least, at least there is some positive to be gained as well in terms of ocean health and ocean quality.
So this kind of information would be very much of interest to policymakers. And yet, in my experience, they're easily confused, especially with complex stories like yours, and in fact, sometimes nefarious in the selection of stories and ideas, advancing their own political purposes. How do you present this kind of information to them in a way that leads to constructive outcomes? I mean, from what you've shown us, I would expect them to be all over tree planting, but I haven't seen it.
A very good question, and I think that we're bad at this as social scientists. A lot of our policy prescriptions too complex. But also at the same time, as most policymakers aren't taking the time to read science, and so we had a really illuminating discussion a few years ago with the Parliamentary Office of Science and Technology. They advise UK Parliament on science and technology issues, and they write all these reports on geoengineering, genetically modified crops. All these other neat technologies. And we asked them, when is the last time you read an academic study? 2 of them said 10 years, and 1 said never. And then I said, well, what are you reading? Press releases, blogs, and newspapers, like the Financial Times or The Economist. So it's kind of like they're not even bothering. And all 3 of these analysts had PhDs, by the way. So that does kind of imply that it's like they're not going for input from where we publish on Science Direct, Scopus, and the Web of Science. And it's very hard to have an impact because the answers we give are very complex and they can't be politically manipulated to just give one simple answer. That said, I do think there are some no regrets or low regrets options like done well afforestation, ecosystem regeneration, better soil management that do have lots of benefits. But I think in the end, and this is why we're triangulating our interview data and our expert elicitation data with the surveys and the focus groups, is because we want to see, that's what the experts had said, what about what the public says? And can we find that intermediate ground of options that are technically sound, scalable, cheap, but also have social legitimacy? And that will differ by region, by country, by part of the world. And I think that's where we'll get into very nuanced policy prescriptions. We can go to Nigeria and say, okay, here's the kind of portfolio of options we think are best for you with all these criteria. But for Singapore, it's very different. And for South Korea, it's very different. And for Australia, it's even more different. And so I think it's kind of we're not there yet to be able to give that type of specific policy advice, but we should be able to, given our data, in about a year. But if you want to help with that, we're always looking for advice.
Okay, we'll take one more. Okay, then maybe I can ask one last question. So hearing what you say, when do you then expect this kind of additional, because when it comes to CO2 reduction, still we are clinging to 2 kinds of technologies, mitigation, adaptation. All the additional technologies, what do you think they go into the official lexicon of global climate change negotiations?
So there are some who argue that actually most of these options could still fall under mitigation or adaptation in different ways. Direct air capture, if it's coupled to offshore wind or hydrogen, is mitigation. It's making your mitigation option more profitable. There are others who say it's anti-mitigation because it's all going to enhanced oil recovery, so it's actually countervailing, what your mitigation goals are. And same with adaptation, right? Things like ecosystem restoration and reforestation, that's kind of just adaptation, like building resilience and replanting trees. And so the kind of definitions do get a bit blurred. So that's one perspective. There's another perspective that says, no, these options are so fundamentally different in terms of their permanence, their reversibility, and the way in which we're intervening in the climate, that they deserve their own classification. And I've even heard, I don't think this will go this way, but I've even heard that we should have a 4th working group of the IPCC. The first is climate science, the second is adaptation, the third is mitigation, and the 4th is these, geoengineering. And they deserve their own different assessment and classification because they're so unlike the other options. The other 2 things in which it's interesting is that some of these options are very new, like sprinkling aerosols and sunshades, but others are very old, like ocean, afforestation and soil management we've been doing for thousands of years. So these aren't really new technologies. And the other distinction we like to make a little bit is hard and soft. Amory Lovin's famously talked about hard energy sources are like centralized, fossil fueled, don't really care about energy services quality, brute force. And soft options are decentralized, renewable, non-depletable, and really care about the quality of energy use. And we think the same thing's happening with carbon removal and geoengineering. Some options are very, very soft, like micro-scale forestry or even decentralized DAC could be very good, like very small scale, community can own them and operate them. You could have a DAC plant on every hospital, on every church, run by these different communities getting carbon credits. Or in Ministry of the Future, a book we were talking about, small scale people getting paid to sequester CO2 in their garden. And they get paid a few, you know. In societies that live on $1 a day, getting $1 of carbon credits per week really matters. So those options are good. And then you have other options like ocean fertilization or high altitude, you know, cloud thinning with fleets of aircraft that are very, very kind of technocratic, hard from the top down. Even forestry you can do that way with genetically modified monocultures, mass forest plantations that kick out, you know, natural forest land and dispossess people. Huge criticism over REDD+, with the way that we've dispossessed indigenous peoples, all in the name of trying to store carbon, and it was just a nightmare where they gamed the system. So I think those types of dichotomies, hard versus soft, natural versus engineered, new versus old, are also important as we think about all of the options.
Okay, thank you. Let's give him a big round of applause. Thank you. We'll take 5 minutes before we begin the next session.
Hello, everybody. Let's start today's fourth and final session. This session is presented by Professor Yang-kook Son of Department of Energy Engineering at Hanyang University. As you know well, Professor Yang-kook Son is not only a professor at Hanyang University, but also a professor and researcher representing Korea. Professor Son Yang-kook worked at Samsung Institute of Technology after he received his PhD degree from Seoul National University. He has been devoted to battery research since he was appointed to Hanyang University in 2000. Professor Son, who is a postdoc chair professor, was selected for the HCR this year, which is a great thing that he was selected for 7 consecutive years. Professor Son has won many top awards, including the Korea Best Scientist Award. Even if I introduce Professor Son, there is no end, so this is it. And I will bring Professor Son to his seat with big hands.
Thank you for nice introduction, Chairman. Today, good afternoon, ladies and gentlemen. And it is my great honor to present this honorable the symposium, first symposium for HY-IEE. And my title is the high energy nickel-rich cathode material for electric vehicles. And this is the prospect of the EV and the LIV market in the futures. And as you can see it here, the global lithium-ion battery size was valued at around $42 billion in 2021. However, the market size greatly increased, projected to reach to around 135 billion in by the 2031. And accordingly, the EV market, electric vehicle sales exponentially increased with the times. And sorry, it's a little confusing. And this is the market share of the cathode materials. And as you can see that high nickel cathode material remain dominant in electric vehicles in the past and in the futures. And this is the map of energy density of cylindrical 1860-50 lithium-ion batteries. As you can see that in 1991, the first generation lithium-ion battery was introduced in the market in the Sony. At that time, the energy density of the energy density is the gravimetric energy density around 100 watt-hour per kilogram, volumetric energy density around 220 watt-hour per liter, which is slightly larger than that of the nickel metal hydride batteries. However, for last 30 years, as you can see, energy density have been increased around only 3 or 4 times. For example, the gravimetric energy density increased around 3 times, volumetric energy density around 4 times. The main reason for this increase in energy density is the optimization of cell design to maximize the packing density of the electrode materials. Of course, the modified negative and positive electrode partially contributed. In order to further linear increase in the energy density, we should develop the high energy electrode material, especially for the cathode materials. And this is the history of the electric vehicles. As you can see that at this moment, we enter generation 3 electric vehicles with a driving range about 500 kilometers. However, consumer wanted a longer driving range. In order to further increase the driving range of around 500 to 800 kilometers, we need a high capacity cathode materials. And this is the content of my talks. First, let me briefly introduce capacity fading mechanism of nickel-rich NCM cathode materials. And this is a major issue of NCM cathode materials. As you can see from the initial charge-discharge curves, with the increasing nickel content, the initial discharge capacity is gradually increased. For example, one-third cathode material deliver the capacity around 160 milliampere per grams. Surprisingly, pure lithium nickel oxide delivered the initial discharge capacity close to 250 milliampere hour per gram, which is close to theoretical capacity of 280 milliampere hour per gram. However, cycling performance is decreased, and also, as you can see from DSC profile, exothermic peaks shifted to low temperature with increasing nickel content accompanied with higher heat generation. For example, the one-third material shows the exothermic peaks around 300, more than 300 degrees Celsius. However, pure LNO cathode shows the exothermic peak around 180 degrees Celsius. In addition, the initial starting exothermic peaks appeared around 150 degrees Celsius. Therefore, it is very difficult for the pure lithium nickel oxide on the practical lithium-ion batteries. This is the summary of this summary with increasing the discharge capacity by raising nickel content from 1/3 to 100%, the capacity retention and the thermal stability accordingly decreased. Based on this result, we believed that it is impossible to develop ideal cathode material by just changing compositions. And however, we need cathode at this point with high capacity, good cycle life, good thermal properties. In order to do that, we should know the capacity fading mechanism of nickel-rich cathode materials. And this is a capacity fading mechanism of nickel-rich cathode materials. As you can see here from the DQ-DV curves, nickel-rich NCM cathode material experience 4 distinct reversible phase transitions during the charge and discharge. This is H2, H3 phase transitions. The extent of the H2, H3 phase transitions depending on the nickel content. In addition, as you can see here, unit cell volume gradually decrease up to 4.1 volt and then decrease rapidly above 4.2 volt, corresponding to effects of the H2, H3 phase transitions. In addition, unit cell volume variation increased with increasing nickel content. For example, this value is 4.3% for NCM622 and 7.8% for NCM90, almost 10% for pure LNOs. From this result, I believe that this anisotropic unit cell volume contraction caused the micro cracking of the cathode materials. In order to verify this hypothesis, we investigate the particle surface of the cathode material by charging to 4.3 volt at the first cycles. As you can see here, NCM811 cathode contains hairline microcracks in the particle core, which is trapped in the particle interiors. However, NCM95 and LNO cathode exhibited increased amount of microcracks, which is propagated to particle outer surface. And in addition, it is well known that parasitic reaction of tetravalent nickel with electrolyte produce nickel oxide like rock salt impurity layer on the particle interior at the highly charged state. And this damage becomes severe with increasing nickel content. And this is a capacity fading mechanism. In the case of a nickel content more than 80%, the formed microcracks resulting from the H2, H3 phase transition propagated to particle outer surface and facilitating electrolyte infiltration along the grain boundary into particle interior, which accelerate surface degradation of the primary particle by reacting unstable tetravalent nickel with the electrolyte to form nickel oxide like the impurity phase, and thus lead to gradual capacity fading with the cyclings. And the relationship between microcracking and the structural change of the NCA cathode are graphically demonstrated by the crystal structure analysis by the in situ XRD and the microstructure analysis using the SEMs. Like the NCM, the NCA cathode material suffer from the volume change. The unit cell volume change increased with the increasing nickel content. For example, this value is 5.6% for NCA80 and 8.4% for the NCA95, which is well consistent with the extent of the H2, H3 phase transitions. And like the NCM case, the unit cell volume contraction caused the microcracking of the cathode active materials. And as you can see from the cross-sectional SM image, the formed microcracks in NCA80 after charge 4.3 volt remained in the particle interior, which is not well connected to a particle outer surface. However, NCA88 and 95 cathode shows the increased amount of microcracks, which is well connected to particle outer surface. Therefore, electrolyte can attack in the particle interior, which lead to capacitive fading. The capacitive fading mechanism NCA is almost similar to NCM case. In order to overcome the capacitive fading, inherent property of the capacitive fading mechanism of nickel-rich cathode materials, our group studied the practical solution, two practical solutions for last 20 years. One is a concentric gradient cathode, the other is a microstructure controlled cathode. And let me introduce the concentric gradient, NCM cathode materials. And this is the development history of the concentric gradient cathode materials. After invented in the core shell material called Generation 1 in 2005, I continuously improved this concept by developing four more cathode materials. And this cathode material licensed by the Korean company and already penetrated into EV markets. And in 2018, Kia Niro used this gradient cathode materials. And in this year, for the F150 Lightning also adopted this cathode materials. And we are expecting our concentric gradient material further enter the electric vehicles. And this is the unique characteristics of the concentric gradient cathode materials. The first concentric gradient cathode material composed of nickel-rich core and nickel-less shells. As explained before, concentric gradient cathode with the nickel poor surface is much stable from the electrolyte attack compared to nickel-rich cathode surface. Secondly, this material composed of contains large-scale morphologies. Large-scale primary particle, as you can see here, very resistant to micro-cracking induced by the internal strain. I will explain the more detail in the importance of the large-scale morphology in the following the materials. And we prepared two different kind of material. One is CSG NCM90. 90 means nickel content. And the other is conventional cathode NCM90 without the concentric gradient materials. This is the long-term cycling performance of two materials. As you can see here, the CSG90 full cell shows the much improved cycling stability of showing the capacity retention 88% versus 68% for the CC90 after 1,000 cycles. In addition, as you can see from the cross-sectional SM image after 1,000 cycles, CC90 cathode particle almost nearly pulverized into their individual prime particles, whereas the CSG90 cathode exhibit the hairline microcrack, which is trapped in the particle interiors. And based on the stress distribution simulation, this is a CC90, this is a CSG90 cathode. As you can see here, encapsulation shell established, exhibited much more homogeneous stress field and the reduced the stress field spread of the microcracks of microcrack formation, and thus CSG90 cathode material maintained its mechanical integrity. In addition, as you can see that XTXM image after 1,000 cycles, almost all edge of the CC90 cathode particle are passivated to nickel oxide rock salt impurities, which has nickel oxidation state of 2+. In comparison, our CSG cathode particle shows the limited surface damage, and the cathode primary particle has a nickel 3 plus oxidized state of layered structures. And also we check the safety test of our synthesized FCG materials. We fabricate the pouch type full cells shown here, with a capacity of 250 milliampere hour in our laboratory, and then we did the nail penetration test and the overcharge test. This is the overcharge. Oh, sorry, what happens? I'm sorry, this is not working. 이걸 I'm sorry, this computer is not working well in the movie operations. Okay. Okay. This is a nail penetration test result. After fully charged to 안 돼. 안 돼. Okay, it's not working well. 안 되는가 봐. Okay. 안 돼. I'm sorry, I cannot. I didn't checking the operation. Oh, okay. 영상 안 되면 돼. Okay. I'm sorry. This is not so working well, and this is the safety test result. Oh, it's working well. Yeah, after charging to fully charged 4.2 volt, the nail is penetrated into the pouch cells. As you can see that the highest, after the nail penetration test, the highest temperature is below 70 degrees Celsius. This is the overcharge test result. It's working. You can see this cell was slowly swollen due to electrolyte evaporation from liquid to gas. And you can see that in the slowly swollen. And after the overcharge test, the cell voltage increased only by 0.5 volt with the temperature remaining below 20 degrees Celsius. Yeah, after nail penetration and the overcharge test, both cells shows no smoke, no thermal running. Yeah, it confirming outstanding safety of our FCG materials. And I'm sorry, a little confusing for you. And recently, we developed the generation 5 cathode material by precision microstructure tailoring. We prepared 4 different kind of cathode material. One is pristine CSG90. The others are the antimony, niobium, and the molybdenum cathode materials. And this is the comparison of a cross-sectional SM image, CSG90 and the antimony CSG90 cathode particles. And as you can see that when CSG90 cathode particle calcined at the optimum temperature of 720 degrees Celsius, it contains radially aligned long rod shaped prime particle. However, when the calcination temperature further increase, primary particle become short and thicker with the increasing lithiation temperature. In comparison, antimony doped CSG cathode prime particle maintains their original rod shape prime particle morphology over the wide temperature range of around 100 degrees Celsius. To quantify the prime particle morphology of the two cathodes, the particle width and the aspect ratio was measured from the cross-sectional SM image. As you can see that in the case of the CSG-9 cathode, with increasing the lithiation temperature from 720 to 820 degrees Celsius, primary particle width increased notably from the 100 nanometer calcined at 720 degrees Celsius and 800 nanometers, which is calcined at 820 degrees Celsius. In addition, the aspect ratio approaches to 1 after calcination 820 degrees Celsius. In comparison, as you can see that the primary particle width of the antimony CSG-9 cathode remained under 300 nanometer and the aspect ratio remains above 3. And in addition, this, as you can see, these figures, nickel concentration of the CSG-9 particle almost flat throughout the particle after calcination of 790 degrees Celsius. In comparison, nickel concentration difference in antimony CSG-9 cathode remained considerably high, even at the calcined 820 degrees Celsius. From this result, we believed that the antimony doping was effective in the suppression of the primary particles coarsening and the interdiffusion of transition metal, especially nickel, from the particle surface to particle core, vice versa. And this is the cycling performance. This is the HEPA cell test result. The CSG-9 cathode reached 720 degrees Celsius exhibit the highest cycling performance with the capacity tension 92% after 100 cycles, but the capacity tension gradually decreased with increasing lithiation temperatures. In comparison, antimony CSG cathode exhibit superior cycling performance. For example, even antimony cathode material calcined 820 degrees Celsius shows the capacity tension 92%, which is comparable to the CSG-9 calcined 720 degrees Celsius. And as you can see, these figures, unlike the CSG-9 cathode, antimony CSG cathode can be produced wide temperature window range of 100 degrees Celsius, which means that the production cost of this material is very cheap compared to CSG-9 materials. Other high valence dopant such as niobium and molybdenum also shows the similar effect. This is long-term cycling performance using the full cells. As you can see here, the CSG, capacity tension of CSG and the antimony CSG pouch type full cell is the 80% and 88% after 1,500 cycles respectively. In addition, moreover, antimony CSG sustained 1,000 more cycles before its capacity reaching to 80%. And this is the TEM image and the top seams image of two cathodes after 1,000 cycles. As you can see here, CSG-9 cathode exhibited thick nickel oxide impurity layer of 20 nanometers. In comparison, antimony CSG cathode contains thin impurity layer of 6 nanometers. And the TEM ADAX line scan image shows that antimony segregated at the grain boundary, which protect the inner primary particles. And this is the top seams image. This is the antimony doped one. This is the pristine CSG. As you can see here, suppression of transition metal dissolution by acid leaching is clearly observed in the antimony CSG9 cathode. From this result, I believe that the antimony ion not only facilitate microstructure tailoring by hindering transition metal migration from particle surface to core, vice versa, but also provide chemical protection against the electrolyte attack on grain boundary exposed to the electrolyte, liquid electrolyte. And let me briefly present the microstructure called the NCM cathode material by the exotopings. As is very well known that, as you can see here, NCA and the NCM cathode composed of radially oriented polygonal shaped primary particles. These microstructures can be modified by the exotopings. And the modified cathode, as you can see here, composed of radially aligned ladder-shaped primary particles by the boron, niobium, tantalum, tungsten dopings. This is characteristics of the ladder-shaped NCM cathode materials. As you can see from the cross-section SEM image, conventional cathode easily develop significant microcracks induced by internal strain during charge. In comparison, ladder-shaped primary particle can effectively dissipate the internal strain and thus minimize the microcracking. In addition, in the case of the conventional cathode, as you can see here, the titled primary particle result in relatively long and winding lithium diffusion paths. However, radially aligned primary particles provide fast straight diffusion path for lithium transport, which increase cycle life and the later capability characteristics. And let me show our typical example. First, we prepare the boron doping NCA cathode materials. Boron doping amount is only 1 mole%. And as you can see here, boron NCA cathode particle has readily aligned long ladder-shaped primary particle compared to pristine NCA cathode. Accordingly, the boron-doped NCA cathode shows much enhanced cycling stability. After the 1,000 cycles, like NCM case, pristine NCA completely pulverized into their primary particles. In contrast, the boron NCA cathode maintained their original morphological features. And this is a contour plot and the DKDV variation to cathode before and after the cyclings. And as you can see here, this is the post cycle. This is the after 1,000 cycles. As you can see that 003 reflection of two cathode exhibit smooth phase transition from H2 and H3 phase during the charging and discharging. You can see there is no difference between two cathodes. However, after 1,000 cycles, as you can see here, 003 contour plot for PNCA no longer shows the H2, H3 phase transition, whereas the PNCA maintained its initial contour plot well compared to that of the post cyclings. In addition, from the DQ-DV curves, H2, H3 phase transition of PNCA after 1,000 cycles almost completely disappeared. However, PNCA exhibit the distinct redox peaks, which shows the increased amount of the cycling performance. And this is the nickel oxidation state of two cathodes after 100 cycles. This is the PNCA and this is the PNCA. As you can see here, the PNCA cathode shows the interparticle boundary were completely passivated by the nickel 2+ impurity phases. On the other hand, the distribution of nickel 3+ in PNCA cathode is uniform, confirming the outstanding cycling stability of these materials. Let me show another example. We prepared various metal-doped cathode materials in nickel-90 cobalt 10% cathode materials. And this is a cross-sectional SM image of the various metal-doped cathode materials. As you can see here, the pristine NC, magnesium, aluminum, and manganese-doped cathode consist of large, equiacute, polygonal-shaped primary particle with random orientations. In comparison, boron, titanium, and antimony and the tantalum molybdoped cathode have that in elongated, readily aligned primary particles. And this modification tends to become stronger with the increasing oxidation state of the dopant, except boron. And also the primary particle width decrease, again, aspect ratio increased accordingly with the increasing oxidation state of the dopant. And the angle of the polygonal shape, the primary particle cathode, ranging from the -90 to 90 degrees. However, as the oxidation state of dopant increased, the distribution angle become narrow, ranging from -20 to 20 degrees, indicating crystallographic texture are well aligned in the radial directions. And this is a long-term cycling performance and the morphological pitch. And as you can see here, aluminum and the magnesium doped pouch type full cell shows rapidly capacity fading with the cyclings. However, tungsten, molybdenum, tantalum doped cathode demonstrate outstanding cycling stability with a capacity tension over 94% after 1,000 cycles. And we believe that this long-term cycling performance is closely related to their microstructural feature, and there is optimum size and shape regions. Therefore, the capacity tension after 1,000 cycles are plotted as a function of aspect ratio, average grain size, and average angles. As you can see that these figures exhibit strong linear relationships between capacity tension and the morphological features. In other words, the high aspect ratio, small grains, and small angle provide high capacity of nickel-rich materials. And from this result, the long-term cycle, the full cell performance clearly demonstrated that the high balance dopant greatly stabilize the microstructure of cathode active materials and thus greatly improve electrochemical performance of nickel-rich cathode materials. And as we can see before, and although boron doping provide long rod-shaped primary particle with radially orientations, the cycling performance of this material is lower than the high valence dopant cathode. We believe that this improvement is attributed to ordering structure, where the ordering, this is ordering structure or long range interchange, ordered interchange of lithium and nickel are observed. Another typical example is a polarin doped gradient NCM cathode material. Polarin doping induced the ordering structure. It shows unprecedented cycling stability up to 8,000 cycles. And this is the final topic of, let me briefly introduce cobalt-free high-capacity nickel-rich layered CSG lithium nickel 9 manganese 10 oxygen oxide materials. And as you know, the most of the lithium-ion cathode material contains cobalt. However, cobalt demand rapidly increase more than 6 times in the next decade, but its supply is problematic because incidence of the child labor in ore mining and the supply chain instability and the price volatilities. This dilemma strongly distribute the cobalt cost. As you can see here, in 2018, the cobalt cost spiked to $90K per ton. Recently, it spiked again to $82,000, which is 3 times higher the expensive as the nickel price. And as you can see that here, cobalt-free NM cathode are cheaper than their NCM counterpart cathode materials. Therefore, NM cathode material will be the very promising cathode material in the near futures. And we prepared 2 cathode material. One is a CSG NM90, and the other is the conventional NM90 cathode materials. This is the EPMA image of the synthesized CSG9 cathode materials. As you can see that the CSG9 cathode has 96% nickel in the core, and while this core is surrounded by 2 micro-sized concentric gradient shell with the outer surface composition of nickel 83%. Furthermore, TEM-ADAX mapping image clearly shows that the concentration of the stable manganese is higher in the particle outer surface region, which completely encapsulate nickel-rich core particles. And as you can see, cross-sectional SM image, CSG NM90 cathode, like the NCM case, the cathode particle composed of tightly packed and long rod-shaped primary particles, whereas NM90 cathode, as usual, composed of polygonal shaped equiaxial primary particles. As you can see here, the primary particle of CSG9 cathode are much thinner with the aspect ratio of 5.6 than NM9 cathode with the aspect ratio 2.2. And this is the angle, as like the NCM case. the angle of the polygonal shape, the NM cathode range from -50 to 50 degrees. However, the primary particle, the angle distribution of the CSG NM9E cathode part angle is much narrow, ranging from the -20 to 20 degrees, indicating strong crystallography well preserved in the particles, in these particles. This is a comparison of the cycling performance at the different cycling conditions. As you can see here, the two cathodes shows the initial discharge capacity, almost similar initial discharge capacity of around 233 milliampere per grams. However, cycling performance are inversely proportional to charging rate, especially for NM9E cathode materials. For example, the capacity retention of CSG NM9E is 8%, 85% for the 1C charging and the 3C charging rate respectively. Both 82%, 76% for 1C and 3C charging rate for the NM9Es. And cross-sectional SM image of the NM9E and the CSG9E cathode particle charged at the 1C rate is shows no difference, showing the only hairline microcrack observed in the particle interiors. However, NM9E cathode charged to 3C rate, as you can see, the numbers of microcracks that propagated the particle outer surface. There is a lot of possibility electrolyte infiltration and degradation of surface in a primary particle. In comparison, CSG9E cathode charging at the 3C rate contains microcracks that are mostly confined in the particle interiors. As you can see, these figures, aerial fraction of microcrack over the NM9E cathode rapidly increase with increasing charging C rate. However, the developed microcrack of the CSG NM9E cathode is relatively homogeneous irrespective of charging rate. And this is a comparison of long-term cycling performance of two cathodes. As you can see here, the CSG NM9E pouch type full cell demonstrate outstanding cycling stability with the capacity retention 90% after 1,000 and 78% after 2,000 cycles, whereas the NM9E full cell delivered the capacity retention 80% after only 1,000 cycles. We checked the elevated temperature and the high C rate, harsh condition, charging C rate of 3C and 45 degrees Celsius. Capacity retention of CSG NM cathode shows the reached 80% after 1,000 cycle versus 63% for the NM9E cathode. In addition, as you can see from the DSC profile, CSG NM cathode exhibited improved thermal properties. And from this result, we believed that these differences were affected not only by mangan-rich outer surface composition, but also by the morphological feature of the CSG NM9E cathode materials. This is a comparison of a cross-section of two cathodes after 1,000 cycles at the different charging conditions. As you can see that in the case of NM9E cathode cycled with the 0.8C charging rate, the cathode particle shows no damage, only contains only hairline micro cracks. However, when cycled NM90 cathode with 30C charging rate, as you can see here, the cathode contains numerous large micro cracks, which is well connected to particle outer surface. In comparison, CSG cycled CSG NM90 cathode with 30C charging rate contains mild micro cracks, which is also confined in the particle interiors. This is the 7 lithium top seams mapping image of the cycled NM cathode, shows the coexistence of the distinct lithium poor and the lithium rich region, indicating inhomogeneous lithium distribution within particles. However, the top seams image cycled CSG NM cathode exhibit relatively homogeneous spatial lithium distribution due to the ladder shape morphological features. And this is my conclusions. It is impossible to develop ideal NCM and NCA cathode just by changing the chemical compositions. High valence dopant such as antimony, niobium, and molybdenum in CSG cathode preserve ladder-shaped prime particle with a strong crystallographic texture. As such, antimony CSG cathode retain 80% its initial capacity for 2,500 cycles. The high valence doped nickel-rich cathode produce radially oriented prime particle even in nickel-rich cathode without a concentric gradient. The modified cathode microstructure dissipate the internal strain and leading to capacity tension 80% after 3,000 cycles. The morphological engineered concentric gradient CSG NM90 cathode preserve homogeneous distribution of lithium ion in the secondary particles and show remarkable long-term cycling performance with a capacity tension 80% after 2,000 cycles. This is our collaborate, especially I really thank the BMW for long-term support for this project. Thank you for your attention.
Okay, thank you very much, Dr. Sun. Do you have any questions? Okay. Yeah.
Thank you very much. As a non-technical expert in batteries, very interested in the future of storage, and I'm curious, you're ruling out some very good batteries that people talk a lot about. By 2030, what do you see as the battery market? Do you think it's going to still be lithium ion, or do you think some of these new innovations could substitute for lithium ion batteries?
Yeah, nowadays in the battery society, we are developing next generation batteries such as all solids battery and lithium metal batteries. However, the research think that lithium ion battery will be continuously used for the EVs for more than, I guess, at least 10 years, at the most 30 years. As you know, the reflection of the development history of the rechargeable batteries. As you know, in 1890, sorry, the lead-acid battery was developed. After 40 years, nickel-cadmium battery was developed. And after that, nickel metal hydride battery was developed after 90 years. Means that it takes around more than 40 and 90 years to develop new generation battery system. I believe that the lithium-ion battery is all might except the safety issues. I believe that the lithium-ion battery will be continuously used for at least more than 10 years, at most 30 or 50 years. Nobody knows. However, lithium-ion battery at this moment the champion. Thank you.
Okay, there. Here.
A very nice talk. Thank you very much. Very informative. I couldn't quite discern if your manganese and antimony doped cobalt-rich batteries were substantially better than the cobalt-free batteries. I think the answer is that the cobalt-free batteries still had lower energy density and higher fade. Do you see them overtaking the cobalt-rich batteries eventually?
Yeah, sure. I believe that nickel. I believe that nickel cobalt-free NM cathode material will be widely used in the futures. For example, as you can see here, this is the energy density of two materials. One is gravimetric, the other is volumetric energy density for the two cathode materials. In the case of nickel 90 cathode material, this is NM cathode, this is the NCM cathode, the cobalt-containing cathode material. As you can see that in the case of nickel contains more than 90%, the energy density is very close. And also, I believe that if nickel contains more than 95%, nickel manganese cathode active material will be more stable than their NCM counterpart. And as you know, the cobalt has a lot of the issue in terms of the price and also in the child labor usings. We are developing the cobalt-free nickel NM cathode material with a nickel content more than 95%, which will be commercialized, I believe, in the future.
When is the future?
Around 2 or 3 years later. Yeah, we are developing. Yeah, thank you.
Okay, any others? Yes. Yeah.
Thank you for the presentation. And today you are showing most of the cathode research, but as everybody knows, the battery has another composite, the anode side. And did you do any research which combination gives us best performance with your different cathode material?
Yeah, very good questions.
You don't like anode?
No. And as you know, at this moment, most of the lithium-ion battery use graphite systems. Graphite, as you know, graphite has the theoretical capacity of 372 milliampere hour per gram, which is larger than that of the NCM and the NCA cathode material. However, in order to further increase the driving range of electric vehicles, we should develop high capacity anode materials too. However, it is very challenging to develop a new anode system such as silicon and lithium metals. However, as everybody knows, silicon has a huge capacity. However, capacity cycle life is very poor. In order to overcome this issue, recently, at the commercial battery, in the commercial battery used composite material by combination of graphite together with the silicon. However, if we use too much amount of the silicon material in composite anode material, cycle life is very poor. We are optimizing these compositions. At this moment, 5% silicon in composite material is satisfy the practical requirement. And nowadays, the research for who developed anode material trying to increase silicon content in this composite, hopefully 10 or 15%, which lead to further increase driving range of the electric vehicle mode, such as 800 or 1,000 kilometers together with the nickel-rich ancient cathode materials. And also the silicon will be hopefully can be used the practical barrier, but it is a lot of challenging. And nowadays, and our colleague is deeply investigate these possibilities.
Thank you.
So another question? Yes, over there.
Thank you for the great presentation. Actually, it was kind of interesting to know about the development of cathodes. And actually, I got one question. In some of your work, you had tried to dope the cathode, the Ni-rich cathode. But it was really interesting when we saw boron doping, it performed better than other metals, because we know that the chemistry of the boron, it's metalloid, and the application of these batteries are at low temperature. So at low temperature, they do not conduct any electricity. So is it something about the boron chemistry or metalloid nature of this, or any other reason for the better activity of this doped material? Thank you.
Yeah, as shown, these are the figures. As you can see here, and even here. And you can see that boron doping doped cathode material shows a slightly lower cycling stability compared to high valence dopant cathode materials. As I explained before, the high valence dopant provide ordering structure, which is very stable at a highly charged state during cycling. However, boron doping cannot provide these ordering structures, even though this material shows, in this case, this material shows radial lined long rod-shaped particles. I believe that the high valence dopant, such as molybdenum tungsten, will be commercialized compared to boron doped material in terms of the long-term cycling performance.
Okay, any other question? If you have, okay, then I think it's time to conclude today's symposium. Oh, no? Okay. Yeah.
Thank you.
Thank you very much.
Thank you for your attention.
And I suggest that we're gonna take a picture again here in front of with this old speakers. All audience come out, and second floor, they stand up here, and we're gonna take a picture. Okay? Yeah. All the audience.